Yes, good morning, everybody. Can you listen to me? Please raise your hand, everybody. Yes, everybody. See, quick review. I will do what we did in the last class, and today also we will extend as much as we can. Please cooperate, sir, because today we will start transients after completion of magnetic circuits. We will definitely start transients. Okay. Now, everyone, look here. Last class we were continuing this dual duality. Here I took a DC steady state problem with dependent source, and so many were asking initially about the polarity and direction. So I told that you have to satisfy the way you write KVL and KCL. See, my set of equations both are exactly same. Okay, that is how I manage the polarities and directions with my notations. In case any student has a different way to write, yes, do this. And yesterday one student also corrected my notes that switch closing in series is dual to switch opening in parallel, or switch opening in series is switch closing in parallel. Okay, that was correct. Now this is the dual AC steady state with dependent source. Okay, then resonance we started. Of course, resonance is the frequency response of a circuit or network when we are operating at its natural frequency called resonance frequency. Okay, these are the definition of resonance. Then it can happen only in circuits where both L and C are there together, and these L and C elements in this chapter are very high quality, and quality factor is defined as 2 pi into maximum stored energy per cycle of supply by energy dissipated per cycle of supply. Another approximate formula for quality factor is reactive power by real power, approximate. And practical designs minimum Q should be 5. Now this is a set of formulas for quality factors. Then the combination of the combined quality factor of practical inductor capacitor. See, what is the meaning of practical inductor and capacitor? That is with resistance. Okay, and that formula is important. Now I gave the gate question there. Then series resonance we started. Okay, series resonance frequency we got here. Then graph about impedance versus frequency, reactance versus frequency, current versus frequency. Okay, phase angle versus frequency. Okay, then phasor diagram under resonance. Okay, these energy oscillations. Okay, graphs relating the voltages and frequency. So maximum voltage at which maximum, okay, the frequency at which maximum voltage appears across capacitor and the frequency at which maximum voltage appears across inductor. Then why power is maximum. Okay, then application, we start application, that is communication bandwidth concept, the derivation of bandwidth. Okay, the corner frequencies, and for high quality, what is approximation. Then a lot of gate bits we did here and there. Okay, and selectivity. Then parallel resonance in that first circuit is general circuit. Here also we got first admittance graph, susceptance graph, current graph, and it is a rejector circuit. Okay, rejector and phasor diagram, and then complete phasor diagram, understanding the energy oscillations here also. And then it is a rejector circuit. Okay, so that is what we have finally declared. It is a rejector circuit. So band stop filter or band rejection filter. Then practical parallel resonance is tank circuit, which is more practical to model with losses. Okay, then ideal tank is without losses. Then this is with both losses in inductor and capacitor. Okay, then dynamic impedance. It is the impedance offered by the network to the source under resonance condition. Okay, now based on this, there are a lot of bits here, and this application of resonance into filter design. Okay, then we started just introduction to magnetic circuit. Okay, that is charges. Now, sir, everybody, please pay attention. Now we are starting magnetic circuits. Yes, charge at rest produce only electric field. That is electrostatics. But charges in motion produce both electric and magnetic fields. Steady state current, steady state DC currents produce time invariant magnetic fields. However, AC currents produce time varying magnetic fields. Now here, right hand thumb rule is the most important requirement here. Dot and cross notation. Okay. Then permanent magnet versus electromagnet notation. Okay. Right hand thumb rule applications in Sarah. Okay. So let us continue from there. Everybody, now please see here. Everybody, now we are continuing from there. I want everyone to please pay some attention here. Okay, so now I'm going with yeah, I'm going with analogy. Okay, yes, analogy between electric circuit and magnetic circuit. Electric and magnetic circuit. Analogy between electric and magnetic circuit. Okay, Everyone? Okay, volume is very low. Now I'll adjust. Please tell me. Now volume is high, sir. Is my volume high? Everybody, please confirm. Yes, is my volume high? Now is it okay, volume? Is it okay, volume now? Now tell me everybody, is it okay? What is happened? Any adjustments? I did not do any adjustment here. Let me check. Is it okay now? Is it okay now? Is it okay now? Nothing is getting adjusted here. In fact, is my volume okay now? Is it okay now? I don't know. Is it okay? Can anyone confirm my volume here? Now I think, is it okay? Okay, let us see. I will take the feedback as we go deep. Okay. Yes, something problem. I don't know. Like suddenly I'm telling you, yeah. Okay. I will take feedback after a few minutes again. Yes, I'm going further. Everybody, please cooperate. Nothing is changed here, sir. But why volume has changed? Nothing. No setting has been changed since starting. Okay, I will find out about this. But I think you can listen now. Okay. Chalo. Now I'm starting this so-called analogy between electric and magnetic circuit. Okay. What is the meaning of analogy? Analogy means similarity. Okay. Similarity. Left side, I'm writing electric circuit versus right side, I'm writing magnetic circuit. Okay. Electric circuit versus magnetic circuit. Okay. Electric circuit versus magnetic circuit. Here, voltage or EMF is the cause. Voltage or EMF is the cause. Its symbol is V. Units are volts. Okay, we already know now, sir. Voltage is the mother of everything in electrical science. Voltage is defined as the amount of work done in moving charge. Okay, na? Voltage is defined as the amount of work done in moving charge. Okay. Voltage is defined as the amount of work done in moving charge. Okay. So here correspondingly, there is something called MMF, magnetomotive force, which is ampere turns NI. Okay, MMF is called what's a magnetomotive force. Like electromotive force, here it is called magnetomotive force, MMF. Now symbol is MMF only, sir, but its units are ampere turns. Ampere turns, AT. Ampere turns, AT. Okay. Voltage or EMF is the cause. Okay. MMF or ampere turns. Okay. MMF or ampere turns. Then in that regard, here current is the effect. Symbol is I, units are amperes. Okay. Here flux, symbol is phi, units are Webers. Okay, Webers, WB I will write, but Webers. Webers, WB. Okay. Like if you give voltage, current flows in a closed path, but here if you give MMF, flux gets established. Okay. Then here there is something called resistance. Okay, resistance is voltage by current. Symbol is R. Units are ohms. Ohms, omega we call. Okay, now here there is something called reluctance, which is mmf by flux. Like voltage by current, it is mmf by flux, that is ampere turn per Weber. Okay, ampere turn per Weber. Okay, symbol is I use special S. So in old EMF books, I'm using special S. Reluctance, I'm using S, special S. Okay, symbol is ampere turn per Weber. Ampere turn per Weber. Like here, voltage by current, there mmf by flux. Okay, now then if I further proceed to fourth point. Now resistance construction formula. Yes, resistance construction formula is R is rho L by A or L by sigma A, where sigma is called conductivity. Okay. Correspondingly here, reluctance construction formula is L by nu A, where nu is called permeability. Nu is called permeability. Okay. Nu is called what? Permeability. Okay. Then in that regard, if I further proceed, now here electric field intensity, voltage by distance. Okay, electric field intensity is voltage by distance. Units are volt per meter. Okay, then here magnetic field intensity is mmf by length, that is ampere turn per meter. Okay, units are ampere turn per meter. Then here electric current density, current by area, units are ampere per meter square. Correspondingly here magnetic flux density, flux by area, which is called Weber per meter square, which is famously known as Tesla. Okay, then Ohm's law. J is sigma E. This is the first form of Ohm's law in electrical circuit analysis. Correspondingly here B is nu H. Okay, B is nu H. So this is the Ohm's law, but actually originally this BH curves, there is hysteresis curves are originally non-linear. Okay, this hysteresis curves are originally non-linear. Okay, yes, this hysteresis curves are originally non-linear, but in my subject I assume there is no saturation and there is no fringing such effects, and hence I say it is a linear curve. In my subject I assume everything is linear, which obeys Ohm's law. So linear transformer, linear inductors we learn here. Then further if I proceed, yes, resistances in series, correspondingly here reluctances in series. Then here resistances in parallel is like 1 by R1 plus 1 by R2. Of course, R1, R2 by R1 plus R2, if you can extend for more. Here also reluctances in parallel. Okay. Reluctances in series. Here also reluctances in parallel. Then correspondingly here, if I go further, I'm giving an example of electric circuit. Like voltage is the cause, current is the effect, resistance can oppose the flow of current. So voltage is the cause, current is the effect, resistance can control the flow of current. And this is electric conductor. This is electrical conductor. What is electrical conductor? Like copper, aluminum wire, etc. Correspondingly here, magnetic circuit I am drawing. Okay, I'm drawing a magnetic circuit. Here magnetic circuit means core material I am drawing. Here important is I draw core material. See, I am drawing a core. Understand, sir? So all the formulas of magnetic circuit chapter, I can first understand by comparing them with electric circuit. No need to derive from EMF. Okay, no need to derive from EMF. We are learning from analogy Analogy is similarity. Okay, analogy is similarity. Okay, so here I am taking a copper wire, winding around it. Okay, and I am allowing a current I. So here ampere turns is mmf. Then what is the effect? Flux is the effect. Okay, flux is the effect. Flux is the effect. Okay, this is the flux. Flux in the core. And reluctance. Yes, reluctance of air is very, very large, which control the flux. Now this is, yes, this is magnetic conductor. Magnetic conductor. What does it mean? Magnetic conductor means magnetic material like silicon steel, okay, iron, etc. Iron, etc. Okay. So all the, everybody please understand. So here all the formulas of electric circuit we can remember. Yes, all the formulas of electric circuit we can remember. Yeah, and also compare the magnetic circuit. So all the formulas what we wrote here, yes, all the formulas what we wrote here, we can compare and remember with magnetic circuits. Okay, there is a concept here. All the formulas what we wrote, we can compare and remember. So quick, sir, everybody. Today we started with analogy between electric and magnetic circuit. Analogy means similarity, comparison. Like here voltage or EMF, here MMF. Okay, current, flux, resistance, reluctance. Okay, and Ohm's law relation is there, like V equal to IR, there MMF is equal to flux into reluctance. Okay, then resistance construction formula, reluctance construction formula, but material is different, sir. So here R is L by sigma A, sigma is conductivity, here reluctance is L by nu A, nu is permeability. But please understand, that material is different. Okay, material is always different. Then electric field intensity, voltage by distance, magnetic field intensity, MMF by length, electric current density, magnetic flux density, Ohm's law in electric circuit form, Ohm's law in magnetic circuit form, resistance in series parallel, reluctance in series parallel, and the simple meaning. See here, the difference you can understand. So magnetic circuit formulas you can remember by comparing with electric circuits. So that is called analogy. Okay, now this is called analogy. Now I am coming to the most important point in this chapter. Yes, I am coming to the most important point in this chapter, and that is Faraday's law. Faraday's law of electromagnetic induction. Faraday's law of electromagnetic induction. Okay, now Faraday's law of electromagnetic induction. Okay. Now statement one. Statement one. Okay, I need not write like this, sir. I need not write like this, but it is same law, but we read as a two statements. Okay. There should be change in, okay, change in flux linkage in a coil in order to induce EMF in it. Okay, there should be change in flux linkage in a coil in order to induce EMF in it. The magnitude of this induced EMF, the magnitude of this induced EMF is proportional to rate of change in flux. Okay, these are the two statements. It is only one law, but two statements are. First of all, there should be change in flux linkage in a coil in order to induce EMF in it, and the magnitude of this induced EMF is proportional to rate of change of flux. Okay, now the magnitude of this induced EMF is proportional to rate of change of flux. Mathematically, yes, mathematically. Okay, mathematically, Faraday's law is given by E is equal to, yes, mathematically, Faraday's law is given by E is equal to minus d psi by dt, where this capital psi is n phi, which is called flux linkages. Flux linkages in Weber turns. Okay, flux linkages in Weber turns. Okay, flux linkages in Weber turns. So if I substitute there, if turns are constant, so this E is minus d by dt of flux linkage, sir, that is n phi. But if number of turns are constant, then E is minus n d phi by dt. This is the mathematical form of Faraday's law in volts. Of course, here this is rate of change in flux in Weber per second. This is number of turns in coil. Negative sign is due to Lenz's law. Is the induced EMF in coil in volts. Okay. Here it is rate of change of flux in Weber per second, number of turns in the coil. Negative sign is due to Lenz's law. Is the induced EMF in the coil in volts. Okay, induced EMF in coil in volts. Okay. Now the same formula I will write it as this E is equal to minus N. Now what is this change in flux by change in time now? So that is flux final minus flux initial by delta T volts. That is the same formula I'm writing like this. Okay, I'm writing the same formula like this. Okay, that is the meaning here. Sangeeta, what is the doubt? You are raising your hand too often. What is your doubt? Sangeeta, what is your doubt? Yesterday also you did this. I will remove you from the class. Please be careful. Yesterday also the same thing happened, Sangeeta. You are often.
Sir, it was before only, sir. At the starting only I have raised.
It is popping up. You have to remove na. After doing once, you have to remove that.
Sir, I forgot, sir. Sorry, sir.
Popping up 10 times now. Now see, this is about Faraday's law mathematically. So, sir, Faraday's law we however learn in machines in so many areas. So no need to worry. But we will do easily the lumped parameter model. Yes, we will learn the lumped parameter model very easy. But the statements I wrote it in mathematical form. But if turns are constant, this is a modern form of Faraday's law, and I wrote here. Okay. Now I'm writing first point, note 1. Now first note is flux is a proportional. Flux is a proportional function of current. Proportional function of current. Function of current. Okay. Flux is a proportional function of current. Now what does it mean? Now see, we know that like V equal to IR, here MMF equal to flux into reluctance. Like V equal to IR, MMF equal to flux into reluctance. Okay, that is Ni is equal to flux into reluctance. Okay, Ni equal to flux into reluctance. Okay, now here if you observe, for any designed system, number of turns and reluctance is always fixed. Once you design any system, the number of turns and reluctance is always fixed. Okay, the number of turns and reluctance is always fixed once you design any system. Yes or no? Then clearly there is a relation between flux and current. So now if I write that ratio of flux by current, yes, ratio of flux by current is turns by reluctance. But this is constant. This is constant. So I will write that flux by current is constant. This is a very important conclusion. So flux is constant into I. So flux is a proportional function of current. Flux is a proportional function of current. Of course, we are neglecting. Yes, we are neglecting saturation effects. Okay, saturation. And I am assuming that BH curve is, what? Yes, BH curve is, yes, I am assuming that BH curve is what? BH curve is linear. Okay. So flux is a proportional function of current. So ratio of flux by current is always constant. And I am assuming that BH curve is linear. Okay, that is the first observation. Second point I am giving. Note 2. Now this you have to answer. See, I am taking an ideal inductor or ideal coil. 2 times I am taking. Okay, in the first case, I am giving ideal DC current. In the second case, I am giving the ideal AC current. Now, you know what is the meaning of ideal AC current? Ideal AC current means sinusoidal. Ideal DC current, you know. Now, options I am giving. Option A. Okay, establishes. I will write here. Establishes flux due to electromagnetism. Electromagnetism. Okay, establishes flux due to electromagnetism. Okay. Then I will also write here. Yes, here I will also write exhibit inductance, exhibits inductance. I will also write induces EMF according to Faraday's law. And fourth option is all the above. All the above. Please understand my question, sir. See, I took here, everybody. I took here 2 coils. Yes, I took here 2 coils. Okay, I took 2 coils here, and one coil I am exciting with yes, DC current ideal DC, and other coil I am exciting with ideal AC. Okay, other coil I am exciting with the ideal AC. Now I am giving some options. For first coil, what is the correct option? And for second coil, what is the correct option? Chalo sir, write the options, everybody. For first coil with pure DC current, what is the correct option? And for second coil for pure sinusoidal AC current, what is the correct option? Yes, no, everybody. Is it audible now? Everybody audible? I had done some adjustments, but is it audible? Okay, everybody, we will go further. Yes. And I did my best, sir. I adjusted maximum level here. I don't know what is the problem. Nothing has been disturbed since yesterday. Okay, let us see. Okay, don't worry, sir. So now see here. Yes, let us come to this bit, everybody. See, I gave two options. I gave an ideal inductor in the first option. Yes, I gave ideal DC. In the second option, I gave ideal AC sinusoid. And I'm asking what is the correct option. So now see, for the first option, yes, it establishes flux. DC current will give DC flux. Okay, na? Yes, everybody, please understand. DC current will give DC flux. That is for sure. But inductance will not get exhibited now because inductance require time variance and no change in flux linkage. So Faraday's law is also not possible. So for the first, only option A is correct. But in an AC sinusoidal, for sinusoidal voltage, sinusoidal current, sinusoidal flux gets established. It also exhibits inductance and there is an induced EMF because of Faraday's law. As there is a change in flux linkage, will induce EMF, and all the above is correct. All the above is correct. Okay, na? So that is the difference you have to understand for ideal DC and ideal AC sinusoid. Okay, that is a big difference you have to understand. Okay, now I'm coming to important concept. Yes, concept of self-induced EMF, and self-inductance. Okay, now self-induced EMF and self-inductance. Okay, concept of self-induced EMF and self-inductance. Now let us consider a coil of N turns. Okay, let us consider a coil of N turns. Okay, yes, excited by a time varying current, Of course, to excite time varying current, I have to give time varying voltage now. So let us say AC voltage only I'm giving. Okay, because AC voltage is time varying. Okay, DC voltage again, inductor is short. Ideal DC steady state current is constant and flux linkage will not change. Then there is no induced EMF as inductor acts like short circuit. But here I am considering a coil of N turns. Okay, excited by a time varying current and time varying voltage. Okay, excited by time varying current and time varying voltage. Now, this MMF ampere turns will establish flux because ampere turns are there. That will establish flux. Okay, ampere turns that will establish flux. Okay, ampere turns that will establish flux. Okay, but now as is the flux is a function of current because current is sinusoidal, flux is also sinusoidal. But how much flux depends upon the reluctance of the path. If you assume this is an air core means no core. Air core means there is no medium or material. That reluctance is high, less flux gets established. But suppose imagine this winding is on an iron core. Okay, imagine this winding is on an iron core, then huge flux gets established. Okay, huge flux gets established. Okay, yes, then huge flux gets established. Then now this flux is a proportional function of current. Like sinusoidal current will give sinusoidal flux. Now this product is change in flux linkage. Okay, So I gave a voltage which is allowing time varying current, which is establishing time varying flux. Now the product is flux linkage. Okay, what is this product? Product is called flux linkages. Okay, the product is called flux linkages. Okay, now yes, the product is called flux linkages. Okay, now there is change in flux linkage will induce EMF. Now according to Faraday's law, this change in flux linkage will induce EMF, and the coil exhibits self-inductance. But this induced EMF in the coil, yes, but this induced EMF in the coil should be such that it opposes the cause. Now, what is the minus of Lenz? What is the meaning of Lenz law minus? See, Lenz law minus says that suppose if di by dt is positive, yes, if di by dt is positive, that means if di by dt is raising, EMF will induce such that it opposes the cause. If di by dt is raising, EMF will induce EMF to oppose the cause. Okay. So now in that regard, everybody listen again. See, I'm considering a coil of N turns, which is excited by time varying current, time varying voltage. Let us say sinusoidal current. Okay. Now this MMF ampere turns, will establish flux. Okay. Ampere turns will establish flux. Okay. Now flux is a proportional function of current. Flux is a proportional function of current. Ampere turns will establish flux, and flux is a proportional function of current. Okay. Now flux is a proportional function of current. Okay. Flux is a proportional function of current. Okay. Now in that regard, now there is a change in, because flux is also sinusoidal. Now there is a change in flux linkage. That is flux into turns is called flux linkage. Now there is a change in flux linkage. The coil will induce EMF in it, but this induced EMF should be such that it should oppose the cause. That means if di by dt is positive, I will write the condition here. If di by dt is positive means raising. If di by dt is positive, current is raising, then this is the correct polarity of the voltage. But if di by dt is negative, okay. But if di by dt is negative, okay, that means if current is falling, then induced EMF will be ulta polar. That means if current is rising, this voltage will oppose the supply. If current is falling, this voltage will aid the supply. That is the meaning here. And the coil exhibits what? The coil exhibits what? Inductance. Okay, the coil exhibits inductance. Okay, it is simple, sir. Okay, now, yes, this is only self-inductance in the coil. That means I am talking with the same coil and its flux. So now let us derive that. Now here, you know, I will write flux is equal to flux, but I will multiply and divide with current in the right side. It is same meaning. Okay. So flux is equal to flux by current into current. Now we know this is constant. Okay. Ratio of flux by current is always constant in any linear magnetic circuits. Now for small incremental change, any complex system can be linear now. So I differentiate for small incremental change. That is phi by I into di by dt. Di by dt. Phi by I into di by dt. This is equation 1. Okay, this is equation 1. Okay, if d phi by dt is phi by 8, but also according to Faraday's law, what is E is minus n d phi by dt now? Yes, that is also Faraday's. Now if I substitute 2 in 1, okay, substitute 2 in 1, substitute 2 in 1, then this E is, okay, E is minus n, okay, minus n, that d phi by dt I will write as phi by I into di by dt. So if I write neatly, this E is minus n phi by I into di by dt. So this is the expression for self-induced EMF. This is called self-induced EMF in volts. This is called self-induced EMF in volts, where this I will write further as E is minus L di by dt. Okay, minus L di by dt, where L is n phi by I. Now this is called self-inductance in Henry. This is called what? Self-inductance in Henry. Okay, this is called self-inductance in Henry. Okay, that is called self-inductance in Henry. Okay, now yes, self-inductance in Henry. Now if I go further, yes, if I go further, now the same here, this I will write it as L is, now this n phi is called flux linkage as psi by I. So this psi is Li. You see that the third form of Ohm's law coming from this here. This is the third form of Ohm's law. You remember we studied in the first class, okay, Ohm's law. That is coming from this chapter actually. Okay, and the same formula, this E is minus L into change in current, I final minus I initial by delta T. I final minus I initial, okay, by delta. Okay, volt, same formula. Okay. Now, if I further expand, we know that V equal to V is MMF, V equal to IR. Like that, I will remember. I is flux, R is reluctance. So Ni equal to flux into reluctance. But what is the correct expression for current? Now, correct expression for current is N phi by L. So this is N phi by L is equal to flux into reluctance. Now, if I remove this, yes, if I remove this, so this L is N square by reluctance. Okay. So conclusion is inductance is proportional to square of turns. Inductance is proportional to square of turns. Also since we know reluctance is L by nu A, okay, length of iron material, etc. Now, if I substitute here, then this L becomes N square by L by nu A. So you will get this as nu N square A by L Henry. So this is a construction formula of inductance. So all these formulas actually come from this chapter. Okay, all these formulas come from this chapter. So what I told, I took a simple coil of N turns excited by time varying voltage, time varying current, which is establishing time varying flux. Now there is a change in flux linkage with the coil in order to induce EMF. That EMF induced should be such that it opposes the cause. If di by dt is positive, that is why I wrote at the bottom. I wrote at the bottom that if di by dt is positive, this is the correct polarity of induced EMF. Because current is rising, it will oppose. But if di by dt is negative, then EMF will aid the supply. If current is rising, it will oppose. If current is falling, it will aid. That is the meaning there. Okay, that is the real meaning of Lenz law minus. Lenz law minus is not polarity. Lenz law minus is to say for every action there is equal and opposite reaction. Okay, now then I derived this. Okay, this is a small derivation. So I derived the expression for self-induced EMF and self-inductance. Okay, from that we observed Ohm's law and also all the constructional formula for inductor. Okay, now I'm going further. Concept of mutually induced EMF and mutual inductance. Okay, concept of mutually induced EMF and mutual inductance. Now, self-inductance is an independent property of the coils. Okay, always remember self-inductance is an independent property of the coil, but mutual inductance is when there is an interaction between at least two or more than two coils. Okay, mutual inductance is at least when there is an interaction between two or more than two coils. Okay, so now let us consider two coils which are placed close to each other. Coil 1, coil 2, let us say of turns N1 and turns N2. Okay, turns are N1 is to N2, let us say. Okay, turns are N1 is to N2. I will write here. N1 is to N2. Okay, let us consider two coils. Let us say they are air core coils. That is why I'm not showing any symbol there. Let us say, okay, air core. Now, out of these two coils, I am exciting only coil 1. Let us say I'm giving current only to coil 1. But here current in this is 0. Let us say I2 is 0. That means coil 2 is not excited, but only coil 1 is excited. Now there is MMF only in coil 1. Ampere turns N1 I1 is called ampere turns of coil 1. But in coil 2, because current is 0, there is no flux established. So because there is MMF in coil 1, that will establish flux. Because there is MMF in coil 1, that will establish flux. Because there is MMF in coil 1, that will establish flux. Let us say this is total flux phi 1. Let us say this is total flux phi 1. Okay, total flux phi 1. Okay, see what I'm trying to write is, yes, let us say this is total flux phi 1. Total flux phi 1. Now, this total flux phi 1, I will now separate to two parts. One is phi 11 and phi 12. Okay, phi 11 plus phi 12, where this is called total flux established by coil 1, out of which phi 12 is the flux linking coil 2. That is common flux or mutual flux, which is linking coil 2, mutual flux. And this phi 11 is that flux which is not linking coil 2, which is called leakage flux. Leakage flux It is not necessary that all flux lines link coil to mass. This is called leakage flux. Okay, now everybody please understand this, everybody. See, yes, I am considering two coils. Yes, I am considering two coils which are placed close to each other. I am considering two coils which are placed close to each other. Okay, I am considering two coils which are placed close to each other. Okay, but they are not electrically connected. Let us say they are air core coils. But in that two coils, only coil 1 I am exciting, which is establishing total flux phi1. But out of this total flux phi1, a part of flux links coil 2. Okay, that is phi1 2. But a part of flux is not linking, that is leaking. Now I will write here, this phi1 2 is a fraction of total flux phi1. This phi1 2 is a fraction of total flux phi1, where k is a value ranging from 0 to 1. What does it mean? If k is 1, let us say k is 1, then total flux is linking coil 2, then there is no leakage flux. Then phi1 is 0. But if k is 0, if k is 0, that means no flux line is linking coil 2. That is also not possible case. So I say this mutual flux or common flux is a fraction of total flux. Okay, this mutual flux or common flux is a fraction of total flux. Okay, now, so in that regard, if I say yes, mutual flux or common flux is a fraction of total flux, that k is a factor ranging from 0 to 1. If k is 1, total flux of coil 1 is linking coil 2. Okay, if k is 0, there is no flux linking coil 2. Okay, that is the meaning there. Okay, so like imagine, sir, if suppose 1000 flux lines are coming, let us say phi1 is 1000. Let us say phi1 is 1000, out of which 800 flux lines are linking coil 2. Phi1 2 is 800. So out of total 1000 flux lines, okay, 800 flux lines are linking coil 2 and 200 are leaking. So then what is phi1 2? 0.8. 0.8, na? That is the meaning there. That is the meaning. Like that you can understand. Okay, na? Yes, that is the meaning. Okay, na? Chalo, now, sir, now let us understand this Faraday's law. Now, out of this flux, which flux will induce EMF in coil 1? The flux phi1 is induced. That part is over. Self-induced EMF is already over. Okay, the change in flux produced in the same coil because of its own current is called self-induced EMF. That is E1. That is E1 here I will write. And this coil exhibits L1. That part is over. Okay, previous section itself, that part is over. Okay, so here also that self-inductance concept is over, sir. Here also that self-inductance concept is over. Please understand. Yes, here also that self-inductance, self-induced EMF over, but I am talking about mutual inductance. Now see, as a part of flux from coil 1 links coil 2. Okay, as a part of flux links coil 1. As a part of flux links from coil 1 to coil 2. Now there is a change in flux linkage. Yes, there is a change in flux linkage. That is N2 into phi1 2 is called change in flux linkage in coil 2. Na? N2 into phi1 2 is called change in flux linkage in coil 2 will induce EMF in it. Now this induced EMF in coil 2. This induced EMF in coil 2 because of the change in flux coming from coil 1. This induced EMF in coil 2 because of the change in flux coming from coil 1 is called mutual induced EMF, and both coils together, yes, both coils together exhibits mutual inductance. Yes, this EMF induced in coil 2 because of the change in flux coming from coil 1 is called mutual induced EMF, and both coils together exhibit what, sir? Mutual inductance. Okay, now let us derive that. Now here for that I will take phi1 2 because which flux is establishing that mutual voltage? This common flux, na? Phi1 2. I will again write phi1 2, but I will interestingly divide by I1 and I1. Okay, now if I regroup it, phi1 2 equal to phi1 2 by I1 into I1. Okay, phi1 2 by I1 into I1. But this is again a constant because ratio of flux is flux by current is always constant now. Yes, constant. Okay, now if I apply linearity for small incremental change, that is d phi1 2 by dt is equal to phi1 2 by I1, phi1 2 by I1 into di1 by dt, di1 by dt. Okay, then also according to Faraday's law, this E2 will be what? E2 will be what? This E2 will be minus N2 d phi1 2 by dt. That is 2. Okay, minus N2 d phi1 2 by dt. Now if I substitute 1 into this E2 equal to, okay, minus N2 phi1 2 by I1 into di1 by dt. Okay, E2 will be minus N2 phi1 2 by I1 into di1 by dt. di1 by dt. So this E2 will be, okay, minus, okay, this is N2 phi12 by I1 into di1 by dt. The same thing I'm writing. Okay, let me not repeat again. Okay, the same thing I'm writing here. So this minus I will take outside. Same thing. Okay, minus N2 phi1. So this E2 is minus M12 into di1 by dt. This is the expression for mutually induced EMF. Mutually induced EMF in volts. Mutually induced EMF in volts. And this M12 is equal to N2 phi12 by I1. But phi12 is K phi1 now. That is K phi1 N2 by I1. K phi1 N2 by I1. This is called mutual inductance. This is called mutual inductance in Henry. Mutual inductance in Henry. So please understand this. Yes, please understand this. Okay. Please understand concept of mutual induced EMF and mutual inductance. Okay. Concept of mutual induced EMF and mutual inductance. Okay. So I am considering only coil 1 is excited and we are finding voltage in coil 2. Yes, that is the meaning there. Okay. So this is the voltage in coil 2 because of the change in current coming from coil 1. And this is called mutual induced EMF. Now what about the vice versa? Now also vice versa. Also vice versa. What does it mean? Now imagine that you are exciting coil 2 but finding voltage in coil 1. Okay. Then directly I will write here let phi21 is K phi2. Phi21 is K phi2 where K is again a fraction ranging from 0 to 1. What does it mean? Now imagine that here we are assuming phi12 is a flux linking coil 2 because of the total flux established by coil 1. Now imagine the vice versa. Now imagine I2 is existing, I1 is 0. Now imagine I2 is existing, I1 is 0. Then phi21 is K phi2 where it is a part of flux linking coil 1 because of the total flux coming from coil 2. That is the same meaning here. Okay. Then directly I will write directly. All this explanation is valid, sir. Directly these expressions I will write. This E1 is minus M21 into di2 by dt. This is also expression for mutually induced EMF. And M21 will be, okay, M21 will be same like this. That is N1 phi21 by I2. Okay, N1 phi21 by I2. But what is phi21 K phi2 now? That is K phi2 N1 by I2. This is also mutual inductance. Okay. So previously I assumed coil 1 excited, we are finding voltage in coil 2. Now assume that coil 2 is excited, we are finding voltage in coil 1, and that expressions will be like this. Now I'm writing a very important note that, yes, very important note that if distance between the coils, if distance between coils, okay, if distance between the coils and permeability of medium is constant, okay. If distance between the coils and the permeability of the medium is constant, then yes, then M12 is equal to M21. Okay. Yes, M12 will be equal to M21. Let us say that is equal to M. See what I'm trying to say, this ratios, that is K phi1 N2 by I2. Okay. This is I1, sir. Please correct it. Yes, let me correct it. That is correct. This is I1 only. Okay. See, phi12 is K phi1. So K phi1 N2 by I1. Okay. And this is K phi2 N1 by I2. Okay. Now these ratios will be same. Provided the condition is what? Yes, if the distance between the coils and the permeability of the medium is constant, then these ratios are constant. Let us say both M12 equal to M21 is M. Okay. Then I'm writing all together. Just to understand, I'm writing all together. Let us say two coils are there. Okay, both are placed close to each other. Let us say N1 is to N2. Okay, now here, okay, let me write like this. Okay, N1 is to N2. Okay, now here I'm exciting both the coils now. Okay, I'm exciting both the coils. Let us say this is I1 and this is also I2. Okay, now this is establishing a total flux phi1 ampere turns. This is also establishing a total flux phi2 and common flux is also there. Then this exhibits self-inductances L1, L2 and also mutual inductance M. Yeah, all parameters I'm showing. Okay, exhibits. So now what are all the formulas applicable here? Yes, we know first L1 is N1 phi1 by I1. This is what self-inductance of coil 1. Coil. What is L2? N2 phi2 by I2. This is self-inductance of coil 2. Then M. M is K phi1 2 by I1, which is also equal to K phi2 N1 by I2. Both are same. Okay, that are all the formulas. Okay, L1, L2, M, all formulas. Okay, na? Chalo. Now relation between them. Yes, now relation between. See, first you have to learn this mathematics, sir, and then only we can do problems. Problems are very interesting in this chapter. Okay, relation between self and mutual inductances. Relation between self and mutual inductances. Okay, yes, if I go with self and mutual inductances relation, okay, this M I am taking two sides. Okay, this M is there are two formulas, two ratios, so I am taking two times M into M. K phi1 N2 by I1, K phi2 N1 by I2. This M square equal to K square into N1 phi1 by I1 into N2 phi2 by I2. I'm reshuffling them. But we know this is what L1, this is L2 now. So this M square is K square into L1, L2. Okay. So this M is K root L1, L2. This is the formula. Okay. That is the relation. Now this K is officially M by root L1, L2. It is called as coefficient. Yes, coefficient of coupling. Coefficient of coupling. Okay, now this K is called coefficient of coupling. Practically, K ranges from 0 to 1. K ranges from 0 to 1. So M is less than or equal to root L1, L2. Okay, M is less than or equal to root L1, L2. Then only in ideal transformer. In ideal transformer concept. Okay, in ideal transformer only concept that K is 1. There is no leakage flux. Then I can say M is equal to root L1, L2. Only in ideal transformer, there is a concept are practically not possible. Okay, practically not possible. Now I'm writing energy expression for energy stored. Yes, energy stored in a system. Yes, energy stored in a system of two mutually coupled coils. Okay, energy stored in a system of two mutually coupled coils. Okay, energy stored in a system of two mutually coupled coils. Okay, na everybody understand this? Yes, energy stored in a system of two mutually coupled coils. So now again I am considering, yes, for representation two coils which are coupled together. Let us say I1 is the current flowing in coil 1, I2 is the current flowing in coil 2, L1, L2 and M is there. L1, L2 and M is there. Then this energy total will be half L1 I1 square plus half. Okay, let me write this side. For me, it is easy to explain. Yes. Then the total energy stored in this mutually coupled coils is half L1 I1 square plus half L2 I2 square plus and minus M I1 I2 joules. Plus and minus M I1 I2 joules. where plus is called for mutually adding flux, mutually adding flux. Minus is for mutually opposing flux. Okay, plus is for mutually adding flux and minus is for mutually opposing flux. But we cannot see flux lines now, sir. But if both the coils are establishing flux to orient, yes, if both the coils are establishing flux to orient such that they are adding, yes, then it is plus you have to take. But if coils are establishing flux to oppose, then it is minus. Now this is interesting. Okay, now how to determine that? Yes. Now I am writing a very important note. This is important, sir. Dot convention is coming. Mutual inductance. Mutual inductance is always, okay, mutual inductance yes, mutual inductance is always a positive quantity. Okay, everybody, mutual inductance is always a positive quantity. Okay, positive quantity. Okay, now mutual inductance is always a positive quantity, but mutually induced EMF can be positive or negative, can be positive or even negative Okay, na mutual inductance is a parameter, passive parameter. It is always a positive quantity, but mutually induced EMF can be positive or negative. But determining the correct polarity, okay, determining the correct polarity of mutually induced EMF is not possible directly. Okay, determining the correct polarity of mutually induced EMF is not possible directly. Hence we use dot convention. Okay, determining the correct polarity of mutual voltage is not possible directly. Yes, determining the correct polarity of mutual voltage is not possible directly, and hence we use dot convention or dot notation. Okay, hence we use dot convention or dot notation. Okay, what is this? So first of all, for dot convention, there is something called polarity test or kick test, sir. Electricals we know, in transformer we do. Okay, based on that test, we are writing the statements. Okay, dot convention statement 1. Okay, this is statement 1. Statement 1. Okay, what is this statement 1? If current enters the dotted terminal of first coil, then the polarity of mutual voltage is positive at the dotted terminal of second coil. If current enters the dotted terminal of first coil, then the polarity of the mutual voltage is positive at the dotted terminal of second coil. Statement 2. Statement 2. If current leaves the dotted terminal of first coil, then the polarity of mutual voltage is negative at the dotted terminal of second coil. So please understand. First statement, if current enters the dotted terminal of first coil, then the polarity of the mutual voltage is positive at the dotted terminal of second coil. Okay, now if current enters the dotted terminal of first coil, then the polarity of the mutual voltage is positive at the dotted terminal of second coil. If current leaves the dotted terminal of first coil, the polarity of the mutual voltage is negative at the dotted terminal of second. Okay, that is the meaning there. That is the meaning. Okay, now let us understand this by taking. Okay, what does it mean to prove this? Yes, to prove this, let us take questions to understand. Okay, to prove this, let us take question to understand. Okay, now let us take question to understand this, everybody. Okay, now I'm giving a question. Okay, I'm giving a question. That question is determine the correct polarity and magnitude of mutually induced EMF. Determine the correct polarity and magnitude of mutually induced EMF. Okay, with respect to the given reference. Okay, with determine the correct polarity and magnitude of mutual voltages. Okay, mutual voltages or mutual induced EMFs with respect to the given reference voltage. Okay, with respect to the given reference voltage for the coils below, using dot convention, using dot notation or dot convention. Okay, first I will give two here. So here I need you to write E2. Here again I am giving the second bit. This is I2 and I need you to write E1. Okay, so now read the question carefully. See, first of all, yes, I will review now. Everybody listen to this, please. Everybody listen here. I want everyone to listen here, please. See, mutual inductance is always a positive quantity. Okay. Yes, mutual inductance is always a positive quantity, but mutually induced EMF can be positive or negative. To determine the correct polarity of mutual voltage, it is not possible directly, and hence we are using what? Dot convention. Now, what is this dot convention statement? Actually, after doing polarity test or kick test, everybody, after doing polarity test or kick test in transformer, we get the dot. Okay, now the dots we are exploring, that if current enters the dotted terminal of first coil, then the polarity of the mutual voltage is positive at the dotted terminal of second coil. And if current leaves the dotted terminal of first coil, then the polarity of the mutual voltage is negative at the dotted terminal of second. Now I am giving the question. Determine the correct polarity and magnitude of mutually induced EMF with respect to the given reference voltage for the coil shown below. That means he gave already E2 reference he gave, sir. If it is correct with dot convention, plus answer will come. But if it is wrong with respect to dot convention, minus answer. Okay, if it is correct with respect to dot convention, plus answer. But if it's wrong, minus will. Okay, like that you have to take. Now, see this. Now here, excitation coil is first coil. So don't always misunderstand that I1 is always first. No. Here, excitation is in the left side. So left side is first coil. Here in the second example, right side is the first coil. Okay, always remember, excitation is the first coil. Response is the second coil. Okay, na? Yes, excitation is the first coil. Response is the second coil. Okay, na? That is what you have to understand. Excitation is first coil. Response is second coil. So now in that regard, everybody, if you observe, now you see here. Here current is going this way, na? Yes, if current is entering the dotted terminal, yes or no? Yes, here current is going this way clockwise, but dot is in the entering side now. So if current is entering the dotted terminal of first coil, yes, if current is entering, I will say, yes, if current is entering the dotted terminal of first coil, then the polarity of the mutual voltage is positive at the dotted terminal of second coil. If current is entering the dotted terminal of first coil, then the polarity of the mutual voltage is positive at the dotted terminal of second coil. Now, luckily here both reference polarity given and our dot convention are matching. So answer will be plus. Answer will be plus M di1 by dt. That is the answer. Now see the second example, everyone. See here current I2 is going this way. Current I2, that is the first coil here. Excitation coil is first coil. Current I2 is going, but dot is in the leaving terminal of the inductor. Now dot is in the leaving side terminal of the inductor. Dot is in the leaving side of the inductor. So if current leaves the dot terminal of first coil, if current leaves the dot terminal of first coil, then the polarity of the mutual voltage is negative at the dot terminal of second coil. If current leaves the dot terminal of first coil, then the polarity of the mutual voltage is negative at the dot terminal of second coil. Again, both are matching. Yes, answer is plus M di2 by dt. Plus M di2 by dt. Okay, now I am giving two examples where you should write, sir. So now I am giving two more examples and I want you to write. Now I want everyone to write the expression for E2 here. Here also I want everyone to write the expression for E1. Okay, na? Chalo, understand what I told in the previous example, which is first coil, which is second coil, and compare the dot convention polarity with the given reference polarity, then your answer will come. Okay, it is a comparative statement, sir. But actually, who is placing these dots? We have to do something called kick test or polarity test in a transformer. From that we get. But after doing the test, we are applying the condition. So if the given reference polarity is same as the practical, then answer will be plus. Otherwise, it will be minus. Okay. So everyone try to do that. Yes, again listen here. See here, excitation coil is called first coil, response coil is called second coil. So your left side is current going, that is called excitation coil. Okay, left side is where current is going, that is called excitation coil. Okay, now that is called excitation coil. So now current is going this side, anti-clock. Okay, like that. So dot is in the leaving side terminal of the coil for the current. Current is entering here and going here. So dot is in the leaving side terminal of the coil. So if current leaves the dot terminal of first coil, if current leaves the dot terminal of first coil, then the polarity of the mutual voltage should be negative at the dot terminal of second. Polarity of the mutual voltage should be negative at the dot terminal of second coil. So now both are not matching. So answer will be minus M di1 by dt. It is minus M di1 by dt. Okay, minus M di1 by dt. Okay. Similarly here, current is going this side. Current is going this side. Again, entering side. If current enters the dotted terminal of first coil, if current enters the dotted terminal of first coil, then the polarity of the mutual voltage is positive at the dotted terminal of second. Positive at the dotted terminal of second. Okay, if current enters the dotted terminal of first coil, then the polarity of the mutual voltage is positive at the dotted terminal of second. But again, this is not matching. Yes, this is not matching. So answer is minus M di2 by dt. Minus M di2 by dt. Okay, minus M di2 by dt. Okay, that is the meaning here. That is the meaning. Okay. Now, sir, once we understood this dot convention, see, as we do problems, we'll get more clarity, sir. Don't worry about it. Okay. So now I'm writing these things like coils in series. Okay, coils in series. In that A, mutually adding. Mutually adding. This is L1, L2. This is M. So what is this L total? L1 plus L2 plus 2M. Okay, here coils in series but mutually opposing, I will write. Okay, mutually opposing. Mutually opposing. Mutually opposing. So here again L total will be L1 plus L2 minus 2M. L1 plus L2 minus 2. Then I will write coils in parallel. I will tell you the concept. Okay, coils in parallel. Coils in parallel. In that A, mutually adding. Okay, mutually adding. Okay, in that A, mutually adding, that is L1, L2, and this is L. Now here L total will be L1, L2 minus M square by L1 plus L2 minus 2M in the denominator. Now mutually opposing. Only two coils we are taking first, mutually opposing. L1, L2, and this is M. Now our L total will be L1, L2 minus M square by plus 2M. Okay, now let us understand. See here, these two coils are electrically in series and also magnetically coupled. Okay, Yes, please understand that these two coils are electrically in series and also magnetically. Yes, electrically in series and also magnetically coupled. Okay, na? Yes, these two coils are electrically in series and also magnetically coupled. And now in that intention, yes, if they are electrically in series and also magnetically coupled. Now see these. Suppose current is entering from right to left. Let us say current I1 is going clockwise. Then this is entering. So both the both the coil terminals dot is in the entering side for current. Suppose you take current anti-clock also, leaving, both entering or both leaving. So that will be automatically adding. You will get what? Adding. Adding means here plus 2 mA. But suppose you take current here in clock. Here current is entering the dotted terminal. Here current is leaving the dotted terminal. Or you take current anti-clock. One is entering, one is leaving. So one entering, one leaving is called opposing. Okay, one entering, one leaving is called opposing. Then minus 2 mA. Okay, like both entering or both leaving plus 2m, but one entering, one leaving is called minus 2m. Okay, one entering, one leaving is called minus 2m. Okay, that is the meaning here. That is the real meaning of. Okay, yes, that is the real meaning of yes, dot convention. Okay, now in this case, suppose you take current I, you take total current I, it will divide into two parts. Then both the currents are entering the dotted terminal, entering dotted. So entering dotted is called adding. Entering dotted is called adding. Okay, adding. Then this is L1 L2 minus m square by L1 plus L2 minus 2m. Okay, now here again current if I take, it will divide and go this way. So one is entering, one is leaving. So entering, leaving. Okay, entering, leaving. So it is called opposing. Opposing means here plus 2m. Okay, because opposing means less answer. Less answer means plus 2m. Okay, that is the meaning. That is the meaning here. Okay, so yeah, that is what you have to understand here. Okay. Yes. So that is what, please remember that aiding means more answer will come. Opposing means less answer. Here also, that is why adding more answer, denominator minus second. Opposing means less answer, denominator plus second. Okay, that is the difference you have to know. Now, these are not even like derivations, sir. While doing problems, I will explain them. Okay, don't worry. Now, there are small topics like ideal transformer concept in circuit. Ideal transformer in electrical circuit analysis. In electrical circuit analysis. What is ideal transformer concept in electrical circuit analysis? So these two lines indicate core. So this is circuit theory concepts are lumped parameter, where I assume transformer coils are ideal inductors. Okay, I will take them as ideal inductors. Okay, L1, L2, and there is also M. There is also M, and we take dot convention if necessary. And of course, here turns ratio N1 is to N2. Okay. Now, first of all, in ideal transformer circuit theory concept, here K is equal to 1. But what is this K? This K is called coefficient of coupling. Coefficient of coupling. Okay, coefficient of coupling. Okay. Yes, K is equal to 1. Here coefficient of coupling is 1. Okay, that is the first thing. Okay, coefficient of coupling is 1. And then here we take ideal core. Ideal core. Yes, ideal core relative permeability is infinity. Ideal reluctance is 0. Permeability is infinity. Okay, best magnetic conductor material like that. So ideal core reluctance is 0, permeability is infinity. Now because permeability is infinity, because we know L is nu n square by L. So L1 tends to infinity Henry. L2 also tends to infinity Henry, because permeability is infinity now, nu n square we write now. Permeability infinity, so inductance values, and M is also infinity Henry. Okay. Yes, infinity Henry. That is the meaning. That means in ideal transformer, this L1, L2, M are like infinity. And moreover, no losses. Okay, no losses. No saturation. Okay. Yes, no losses, no saturation. Hence, I call this as linear transformer. Hence, I call this as linear transfer. Hence, I call this as linear transform. Now, since inductance is proportional to square of turns, since inductance is proportional to square of turns, so L1 is to L2 is to M. Okay, L1 is to L2 is to M is equal to N1 square is to N2 square is to N1 N2. N1 N2. Then turns ratio. Turns ratio. Okay, turns ratio A means N1 by N2. So if you take turns ratio N1 by N2, that becomes root L1 by L2. Okay, that is also L1 by M, and that is also M by L2. M by L2. Okay, turns ratio A is N1 by N2, that is root L1 by L2, that is L1 by M, that is also equal to M by L2. Okay, now then how to simplify such transformer in circuit theory? Yes, to simplify in electric circuits, in electric circuit analysis or network analysis, okay, we use T model. We use T model, okay, T model or T equivalent representation of ideal transformer. Okay, T model, that is very, very important, sir. To simplify such transformer circuits in circuit theory, we use T model. In that, again, mutually aiding or mutually adding, both means same, sir. Mutually aiding or mutually adding, and B is mutually opposing. Okay, mutually opposing. So here, first I'm taking that meaning here. Mutually aiding or mutually opposite. Now in that regard, this is L1, L2, okay, M, here also L1, L2, M, but here I am taking dots such that both currents are entering, I will take. So that is why I call this as aiding, but here I will take dots such that one is entering, one is leaving. So we call this as opposite. That is the meaning. Then how to simplify this? Yes, this can be simplified into T model like this. And this also can be simplified into T model. There is a mathematical proof which is unnecessary. That is only by verifying the KVL and KCL you can prove. Okay. Now here, this will be plus M. This will be minus M. This will be L1 minus M. This will be L2 minus M. L2 minus M. And this also L1 plus M. L2 plus M. And this is I1, this is I2, and this is I1 plus I2. Here also this is I1, this is I2, and this is I1 plus I2. I1 plus I2. Okay. To simplify in electric circuit analysis, we use T model, sir. See, here both current entering dot called mutual adding. Mutual adding means here plus M will come. Here L1 minus M, L2 minus M. Here one is entering the dot, one is leaving the dot. So it is called mutually opposing. So mutual opposing, here minus M will come. Here L1 plus M, L2 plus M. Okay. So that means two separate circuits electrically. Yes, two separate circuits electrically. Yes, two separate circuits electrically is simplified into, yes, Why proof? I told na sir, proof is not necessary. While doing problems, you will do. You write KVL. You write KVL here, you will get it. You write KVL here, you will get it. If you write the KVL for the first problem, suppose this is V1. What is this V1? L1 di1 by dt. But this is also entering, plus should come, plus m di2 by dt will come. So total voltage V1 will be L1 di1 by dt plus m di2 by dt. You think that I don't know proof, huh? B million is fine. You think that I don't know proof. For fun sake, I teach it. And here you write a KVL again by taking some V1. Here you will get L1 di1 by dt minus m di1 by dt, but m di1 by dt plus m di2. So if you cancel that m di1 and minus m di1, you will get the same equation what we got here. So the KVL and KCL in both cases will satisfy after reduction. What effect this network can give, which is a transformer, is the same effect what we get here. So it is only possible in circuit theory, that too with ideal inductors as transformer. But in machines, it is completely different. Okay, please remember. Now I want to give the contrast. Okay, I want to just give the contrast what we learn in machines. Now this is the difference. See, transformers in machines. Transformer, more practical machine model. Okay, practical machine concept. Practical machines model. Now this is more important. Now these are practical windings. Now these windings are practical. Okay, these windings are practical, where again N1 is to N2 turns. Okay, and core is also there, but still these windings are practical windings. So here these windings have losses. So R1 plus JX1 in AC steady state model. This is R2 plus JX2. And moreover, here source load concept is given. What is source load? Here source is connected. Generally, primary winding is that winding where source is connected. I will take this as V1, which is allowing total current I1. And this is the self-induced EMF E1. Then mutual induced EMF E2 based on the turns ratio. And here this is the load concept. Load. This is the load. Load. And this is I2. And this is V2. Sync concept. Okay. So that is the first major difference that you should know, that in a practical transformer, yes, the windings are considered here. Then here K is different. Now another big difference is here in transformer K is different. This K is what? Which is N2 by N1, which is E2 by E1, which is V2 by V1, which is I1 by I2, which is called what? Voltage transformation ratio. Voltage transformation ratio, which is also called transformer ratio. Transformer ratio. So your dot convention is not exposed. It is there, but we are not showing it specifically. Okay. This K is different to this K. Sorry, in machine what K we wrote? This K in ideal circuit is coefficient of coupling and it is 1. But this K is called voltage transformation ratio or transformer ratio. Okay. And dot convention is not exposed. It is there. Here also everything is there, but it is not exposed here. Okay, that is the big difference. So circuit wise, here pure inductor, here practical winding. That is the first major difference between circuit wise. Pure inductor, here practical winding. Second, this K is called coefficient of coupling. Here this K is called voltage transformation ratio or transformer ratio. Okay. And here ML1, L2 dot convention is not exposed, but here ML1, L2 is ideal transformer. Now here also based on dot convention, aiding or opposing. Suppose here also, suppose I take dots here. Okay. Suppose here also I take dots here. Okay. Dots here. Then this is entering, current entering, then E2 will be like this. Here also you take I2, current entering the dotted terminal of first coil, then the polarity of the mutual voltage should be positive, like that even. So here dot convention is necessary, and based on that we write polarities, etc. But here dot convention is not exposed. Okay. It is all Lenz law, Faraday's law we learn. Okay. That is understood. Phasor diagram we draw, etc. Then in machines, how to simplify this in machines, in machine model, we simplify into single circuit. In machine model, we simplify into single circuit. Yes, in machine model, we simplify into single circuit. Okay, in machine model, we simplify into single circuit by reflection concept by reflection of parameter. Okay, reflection of parameter. Like you know these things now, sir. Like secondary to primary, secondary to primary. Suppose I write like this. R2 here become R2 dash. However, N1 is to N2 and we are reflecting it. Okay. Then, sorry, this is called R2 dash. Let me correct it. R2 dash, secondary reflected to primary. So this R2 dash will be R2 by K square. But what is K here? K is N2 by N1. Remember here. Similarly, what is X2 dash? X2 by K square. And what is Z2 dash? Z2 by K square. Z2 by K square. Okay. Then we can also go primary to secondary. Primary to secondary. Okay. Primary to secondary. N1 is to N2. R1, R1 dash. R1, R1 dash. Okay. So this is R2, R2 dash, that is R1, R1 dash. Now here R1 dash. K square R1. Okay. And X1 dash. K square X1. And similarly impedance Z1 dash is K square Z. Of course, here what is K? K is again N2 by N1. K is again N2 by N1. What is the meaning here? That is the meaning. Okay. So in transformer model, we do like this. Okay. So now we'll start some interesting numericals. I will give break in 2 minutes. But this is the first gate question I want to go with. Yes, everybody. What is L total? Okay, I'm asking what is L total. Everybody, what is L total? I'm asking. This is something like 3 Henry, 5 Henry, 4 Henry. Okay, I'm giving dots like this. These two are mutually coupled with 2 Henry, and these two are mutually coupled with 1 Henry. What is L total? Okay, now see this, sir. Here there are 3 coils in series. I want everyone to pay some attention here. Here there are 3 coils in series. I want everyone please to pay some attention here. Yes, of course, here there are 3 coils in series. Okay, now here there are how many coils? 3 coils in series. But there is a mutual coupling between coil 1 and 2, and there is a mutual coupling between coil 2 and 3. But there is no mutual coupling between 1 and 3. That is not given, means it is understood that there is neglected. It is neglected. Okay, see, the self-inductances of coils are 3 Henry, 5 Henry, and 4 Henry, sir. The self-inductances of coils are 3 Henry, 5 Henry, 4 Henry. But mutual inductance between coil 1 and 2 is 1 Henry. Mutual inductance between coil 2 and 3 is 2 Henry. And mutual inductance between coil 1 and 3 is not given, means it is neglected. Now, in such case, when more than 2 coils are there, don't use formulas. See, we wrote formulas for 2 coils. Yes or no? See here, 2 coils series aiding or opposing, series, parallel aiding or parallel opposing. For 2 coils, there is a formula. Here also we can establish, but don't do. See, if the more than 2 coils are there, don't do formula. Do separately. Apply Faraday's law or KVL. Better I will write KVL. See, what I will do, I will give a voltage V, which is allowing a current I, which is a time varying current. Of course, this is not DC concept. In DC, if you give inductors act like short circuit, so I am giving a time varying voltage V, which is allowing time varying current I. Okay, I am giving time varying voltage, which is allowing time varying current I. Okay, now let us write each voltage separately. Now V1 is the voltage in coil 1. Now V1 is a voltage in coil 1, which has got one self voltage and only one mutual voltage. Why? Because self voltage is there because self inductance. But coil 1 and 2 are only coupled. So there is only one mutual voltage. Now what is self voltage? 3 into di by dt. Now mutual voltage. See, entering now. See, entering means plus 1 di by dt. The di by dt I am not writing. Let us come to that is total 4 di by dt. Now let us come to coil 2. Now let us take voltage V2 in coil 2. Voltage V2 in coil 2. Now if I take voltage V2 in coil 2, here one self voltage but 2 mutual voltage. Here one self voltage but 2 mutual voltage. What is self voltage? 5. Self voltage is 5. Mutual voltage. So entering +1, this entering leaving -2. This is also 4. Okay, because self voltage is 5, but between 1 and 2 entering +1, but between 2 and 3 entering leaving is -2. Okay, now let us come to coil 3. Coil 3, again there is only one self and one mutual. One self 4 di by dt, but there is only one mutual. Entering leaving it is -2. This is 2. So overall, if I apply KVL, the total voltage is V1 plus V2 plus V3. You will get 10 Henry. 4 plus 4 plus 2, 10 Henry. Okay, yes, you will get how much? 10 Henry you will get. Okay, that is very, very interesting, sir. Okay, that is what you have to understand here. Okay, now based on this, I'm giving the IES objective. What is L total here also? Of course, here dot is M12, square notation is M23, and star notation is M31. Yes, everybody here also see now. Everybody see. I gave different symbols for dot convention. Here, everyone, please see. I gave different symbols for dot convention. Okay. Now, different symbol symbolizes. Yes, different symbol symbolizes. So similar models are. Listen carefully again. See, different symbol symbolizes which two are mutually coupled. See, in the previous problem, what happened? Everywhere I gave dot, but I forcefully showed the values of mutual inductance. Like 1 and 2 are coupled with 1 Henry, 2 and 3 are coupled with 2 Henry. Like that I showed. Okay. In the first case, everywhere I pick up to dot, and I told that 1 and 2 are mutually coupled with 1 Henry, and 2 and 3 are mutually coupled with 2 Henry. But here I'm giving different dot symbols. What does it mean that which two coils are coupled? Like for example, what is the common symbol between L1, L2? The common symbol between L1, L2 is dot. Nah, the common symbol between L1, L2 is dot. So I need not show any arrow here. The common symbol between L1, L2 is dot, which is mutual inductance how much? M12. What is the common symbol between L2, L3? The common symbol between L2, L3 is square notation. So mutual inductance is how much? M23. Now common symbol between L1, L3 is how much? Star. Common symbol between L1, L3 is star. So mutual inductance is how much? M31. Okay, like that. So now, sir, here more than two coils are there. I will not take the risk. I will apply, yes, KVL. So let me excite with time varying voltage, which is allowing time varying current. Okay, now in that regard. Now here, let V1 be the voltage in coil 1, V2 is the voltage in coil 2, and V3 is the voltage in coil 3 to get total voltage V. Okay, V1 is the voltage in coil 1, V2 is the voltage in coil 2, and V3 is the voltage in coil 3. Okay, na? Chalo, now in that regard, chalo, V1, if I write first, V1. Here, how many self and how many mutual? One self and two mutuals. One self and two mutuals. Self is L1. Mutual between 1 and 2. Okay, what is mutual between 1 and 2? Mutual between 1 and 2 is entering plus M12. Now mutual between 1 and 3, leaving. That is also leaving dot. Because I took current clock now. Leaving is also adding. That is plus M31. Now let us come to coil 2. Now voltage in coil 2, again there is one self and two mutual. One self and two mutual. What is self? L2. What is self? L2. Mutual. Okay, again mutual between dot entering. Entering is plus M12. Okay, between square leaving entering is minus M31 minus M23. Let me correct it. Minus M23. See, I will explain again. In coil 2, there is one self and two mutuals. Yes, in coil 2, one self and two mutual. Self is how much? L2. Mutual dot entering is plus M12. Square leaving entering is minus M23. Now let us come to coil 3. Yes, in coil 3, there is one self and two mutual. Self is how much? L3. but again mutual. Between 1 and 2 leaving entering minus M23, but between 1 and 3 leaving is plus M31. So now if you apply KVL, yes, V1 plus V2 plus V3 is total V. That is V is L total di by dt. So what is L total now if you do? That is L1 plus L2 plus L3 plus 2M12, okay, minus 2M23 plus 2M31. That is the total. That is the total. That is the total Henry. Okay, that is the answer. This is the total inductance. That is the total inductance. Okay, that is the meaning. Okay, we'll take a break, half an hour break. Okay, let's have half an hour break. Then we'll complete this chapter and start transients today. Yes, everybody, please come back. Can you listen to me? Please raise your hand. Okay, let us continue problems. Everybody, let us continue problems on magnetic circuits. Yes, let us continue problems on magnetic circuits. Now, this is a general question. It is not an exam question. What is LXY? Yes, what is inductance between terminals X and Y? Okay. Okay. What is inductance between terminals X, Y? Now, self-inductances are 4 Henry, 4 Henry, 4 Henry, and 4 Henry. Now, I'm placing dot here, triangle here, and triangle here. And I'm mentioning that dot convention is equal to triangular dot convention, which is 2 Henry. So, what is LXY? I want everyone to see this, please. What is inductance between terminals X and Y? Okay, what is inductance between terminals X and Y? Now, see here, this is only a concept, sir. This is not practically true. Why? Why? Because see, the dot dot convention is given for this 4 Henry and 4 Henry here. That means it is assumed that the flux of this first coil is linking with fourth coil only, but this is skipping these two coils. Similarly, delta delta given here means these two coils are only mutually coupled. These two coils are only mutually coupled. That is an assumption. That means the flux of this is linking this and the flux of this is linking this, but this flux is not escaping to link with the outer inductors. Similarly, this 4 Henry is linking with this 4 Henry only. So that is a concept. Actually, this is not correct. Now here, if you assume current, yes, if you assume current I, this current will go and divide here parallel and again combine and come back, again combine and come back. Okay, this current will go divide, combine and come back. So in this first coil and the last coil, dot is in the leaving side, leaving. Okay, dot is in the leaving side and leaving side. Okay, that is series adding. This is now series adding. Yes or no? That is series adding. Leaving side and leaving side, series adding. But these two parallel opposing. Yes, parallel opposing. Okay, so these two are series adding. Okay, dot here, series adding, and these two are parallel opposing. Why? Because one is entering the delta terminal of the first coil, other is leaving. So when two coils are there, directly I can do here, though 4 coils are there, but he mentioned that these two are only coupled and these two are only coupled. So now we can use formula directly. So now for series adding, what is the direct formula? L1 plus L2 plus 2M na? See, L1 is 4, L2 is also 4 plus 2 into M. What is M? What is M? Yes, it is 2. So overall it is 12 Henry. Now for parallel opposing, what is the formula? L1, L2, yes, L1, L2 minus M square. Again, M is also this, minus M square by L1 plus L2. Opposing means less answer. Less answer means more denominator. Plus 2M, M is again. So this is 16 minus 4, 12 by 12, 1 Henry. So finally, now all together, see, after lumping these two parallel opposing and series adding, now finally LXY will be 12 plus 1, total 13 Henry. Okay, 13 Henry. Okay, that is the meaning there. Okay, 13 Henry. Now I'm giving another question which came in IES objective. Write the complete inductance matrix for coils coupled below. Okay, write the complete inductance matrix. For the coils coupled below. Okay, now see, this is the network he gave. This is coil 1, this is coil 2, this is coil 3. Okay. Now these are the self inductances like 5 Henry, 4 Henry, 6 Henry. Okay. Then these two are mutually coupled with 3 Henry. Then these two are mutually coupled with 1 Henry, and these two are mutually coupled with 2 Henry. And I am giving a direction. This is current I1 in coil 1, current I2 in coil 2, current I3 in coil 3. Because if current direction is not given, then different answers can come. Because the dot convention direction in which current enter will differ here. Okay, so he gave the current directions also. So write the complete inductance matrix for the coils coupled below. Okay, watch the question. I will explain now. Everybody should watch the question first. Okay, everybody. Now see here. C is asking the complete inductance matrix for the system of mutually coils below. Now see, what is my idea? I will write the total voltages in each coil, and in matrix form I will write. See, I will write total voltage in each coil, sir. After writing the total voltage, I will write the matrix form, and from that inductance matrix will come. So now see, now in the first coil, now these are not electrically connected but magnetically coupled. Yes, all these coils are not electrically connected but magnetically coupled. Now in the first coil, how many self and how many mutual voltage? One self and two mutuals. So let us write the voltage V1. Okay, let us write the voltage V1. Self is how much? 5 dI1 by dt. Okay, now 5 dI1 by dt. Okay, but mutual. Now here between 1 and 2, this is entering the dotted terminal, but this is leaving. I2 is leaving the dotted terminal. Na? See, this I1 is entering the dotted terminal, but I2 is leaving the dotted. So minus 3 dI2 by dt. And also if I observe, between 1 and 3, this is entering, this is also entering. Entering dotted, entering dotted. So this is plus 1 dI3 by dt. Okay, this is entering dotted, entering dotted. Okay, plus 1 dI3 by dt. And V2. Now if I come to V2, self and mutual. Self and mutual. Self is 4 dI2 by dt. But two mutuals. Voltage in this because of this entering, leaving, entering, leaving. Minus 3 dI1 by dt. And voltage in is because of this leaving, entering, leaving, entering. So it is minus 2 dI3 by dt. Okay. Then I am coming to coil 3. Coil 3 also one self, that is 6 dI3 by dt. And there are two mutual between 1 and 3. Entering, entering. So plus 1 dI1 by dt. Between 2 and 3. Leaving, entering. So minus 2 dI2 by dt. Okay. Okay, so this is how I wrote, sir. See, in each coil, one self and two mutual. In each coil, one self and two mutual. Self in the first coil is 5 di1 by dt, self in the second coil is 4 di2 by dt, and self in third coil is 6 di3 by dt. But mutuals, if you see, between 1 and 2, one is entering, leaving, so -3. And between 2 and 3, one is entering and leaving, that is also -2. But between 1 and 3, entering, +1. Okay, na? So now if I write this in matrix form, now if I write this in matrix form, see, matrix form, okay, na? Equations if I write like V1, V2, and V3. Yes, V1, V2, and V3 is inductance matrix into di1 by dt. I will write this as I1 dot in state variables, you know, sir, that is I1, I2 dot means di2 by dt, I3 dot means di3 by dt. Now, if I show there, yes, that is the meaning. That is 5 minus 3, 1 minus 3, 4 minus 2, 1 minus 2, this is 6. So clearly now this is the, yes, this is the self-inductance and these are the mutual inductance. Okay, clearly this is the self-inductance and these are the mutual inductance. Okay, so finally this is the inductance matrix, L matrix, L matrix. Okay, self-inductance. That is why you see here very clearly M12 equal to M21, M13 equal to M31, M23 equal to M32. We got the same thing here. That is also true. Okay, na? We got the same thing here.
Audio is okay now? Now audio is okay, everyone? Please tell me, is it okay now? I did add something here, but is it okay now? You reduce your volume from your side. Everyone, please reduce volume from your side. See, in the setting, I changed it to Shure Digital. I don't know what is this, but it is coming now. I think it is okay now, everybody. Can you confirm that? Too heavy, too heavy. See, see, that is what happens, sir. See, I did some setting change. I don't know what it is. I'm not having so much knowledge here. You reduce the volume from your side, na, sir, request. Okay, everyone, please reduce the volume from your side. That will be better. Give me 1 minute. I'm setting it up. Give me 1 minute, just a minute. Now confirm, is the audio okay now? I removed all the wires and did it, sir. That is the reason I asked you to mute. Okay. Yeah, I think now it should be very perfect, sir. Okay, chalo, now. Okay, we got this problem, that is inductance matrix. Now I'm going to very important gate problem. This is a gate 2 marks question. Wonderful problem. Find voltage VAB. Okay, find voltage VAB. This is 80 amperes. $60 amperes. This is 8 Henry, 5 Henry, 6 Henry, 7 Henry, and this is dot and dot. Okay, and this is delta and delta. This is star and star. This is square and square, where dot is 4 Henry, star is 3 Henry, delta is 2 Henry, square notation is 1 Henry. Chalo, find the voltage VAB. Find the voltage VAB. Okay, everybody, please understand this question. I'm giving you 2 minutes. Try something, sir. One of the best gate questions here in dot convention. Observe what currents they are. They are ramp currents, please. Ramp currents. Okay, they are ramp currents. Okay, na? Chalo, I want voltage VAB. I want voltage VAB. Chalo, I'm giving you 2 minutes. Yes, I am going with solution now. Everybody listen now. See, what is the meaning find VAB means? Yes, find VAB means it is understood that A is positive with respect to B. Okay, find VAB means it is understood that A is positive with respect to B. So this is VAB I want. A is positive with respect to B. Okay. In electrical notation, AB means A is positive with respect to B. So this voltage I want. But here, the secondary of the coil is split into three parts. See, the primary coil is total single coil. It is 8 Henry. Secondary is also total single coil, like total 18 Henry, 5 plus 6 plus 7, 18. But it is split into three parts. Okay. And these are the self-inductances given in white color. Okay. Now, rather than writing all voltage, because in the secondary there are a lot of self and mutual, I will write in parts. Now, let this be terminal X and let this be terminal Y. So I will write this total VAB as VAX in the first coil plus VXY in the second part coil and VYB. Like that, three parts I will write. Okay, three parts I will write. But now observe, see, in the first coil current is going clockwise. In the first coil current is going clockwise, but what current it is? Ramp current. When ramp current flows through inductor, what voltage will come? Step voltage. Because V is LdI by dt. When ramp current flows, step voltage will come. Yes or no? Yes, when ramp current flows, step voltage will come. Yes or no? Yes, that is the meaning here. So in the first coil, there is a current, ramp current is going 8T. So V is LdI by dt. If you do differentiation of ramp, step voltage will come. Now in the second coil, though there are three parts, only one part is closed where current is flowing, that to anti-clock, because 60 ramp current. But here current is not flowing, here also current is not flowing, because there is no closed path. So in the first coil, 8 Henry current is flowing clockwise, ramp current will give step voltage. In the second coil also, out of three parts, only second part current is flowing anti-clock, which is ramp current. Okay, ramp current. Okay, now in this regard. Yes, now in this regard. Okay, what we want, yes, now in this regard, we want to write each voltage separately. Chalo, first let us take VAX separately. VAX. Okay, let us take VAX separately. Now if I go to VAX, yes, if I go to VAX, now how many self and how many mutual voltages are there? Here self voltage is 0. Okay, there is no self voltage because no current is flowing now, but there is only one mutual voltage because of delta convention. See, in the first part of the coil 5 Henry, there is only mutual voltage because there is no self voltage because current is not flowing. When current is not flowing, it cannot induce EMF, but there is a mutual voltage coming because of the flux linking from coil 1 to coil here. 8 Henry to 5 Henry, there is a link, delta. So that will be what? Now see, if current leaves the delta terminal, okay, if current leaves the delta terminal of first coil, okay, if current leaves the delta terminal of first coil, then the polarity of the mutual voltage is negative at the delta of the other coil, negative at the delta of the other coil. Okay, but this is positive. See, though current leave delta, this is negative, but this is positive. So it is same as my reference now, so it becomes plus delta is how much? Dot convention 2 d by dt of which current? 8t. So total it is 16 volts. Now let us come to VXY segment. Now listen, sir, this segment VXY coil. Okay, VXY, that is 6 Henry. In this, how many self and how many mutual? Okay, there is one self voltage because current is flowing. Okay, there is one self voltage because of current is flowing. But how many mutual? Though 8 Henry and 6 Henry are coupled and 7 Henry, 6 Henry are coupled, but only 8 Henry can induce EMF in 6 Henry because the current is not flowing in 7 Henry. That means in this coil 2, there is only one self voltage and there is only one mutual. Though 6 and 7 Henry are coupled, 6 and 8 Henry are coupled, but only 8 Henry is excited. Only 8 Henry is excited, but 7 Henry is not excited. So only voltage comes from coil 8 Henry only. So there is only one mutual because of dot. One mutual because of dot. Why? Because though square is having dot notation, but 7 Henry cannot induce EMF in 6 Henry because there is no current flowing there. But in 8 Henry, current is flowing. Chalo, first self is directly how much? LdI by dt, 6 into d by dt of 60. Okay, 6 into d by dt of 60. Similarly, now I need voltage in 6 Henry because of current in 8 Henry. Voltage in 6 Henry because of current in 8 Henry. Now dot convention. If current enters the dotted terminal of first coil, then the polarity of the mutual voltage is positive at the dotted terminal of second coil. If current enters the dotted terminal of first coil, then the polarity of the mutual voltage is positive at the dotted terminal of second coil. But again, this is luckily matching. Yes, this is matching. So this is plus dot is how much, sir? Dot is how much he gave? 4 d by dt of which current? D by dt of which current? Primary current 8t. So this is 36 plus 32, 68 volt. Now let us come to the last segment, VYB. Now this is interesting, sir. In VYB, how many self and how many mutual? Self voltage is 0 because current is not flowing. Self voltage is 0 because current is not flowing. But there are two mutual voltages now because this square is coupled and star is also coupled. Square is coupled and star is also coupled. Okay. So please understand. Yes, here everybody. Yes, There are two mutual voltages in 7 Henry, but there is no self because both the primaries are excited. That is why 7 Henry cannot induce EMF in 6 Henry, but 6 Henry can induce EMF in 7 Henry because that is excited. So one mutual because of star notation and one mutual because of square notation. So first star, if you take, yes, if current enters the star terminal of first coil, if current enters the star terminal of first coil, yes, if current enters the star terminal of first coil, then the polarity of the mutual voltage is positive at the star of the second coil. But this is opposite to my asked polarity VAB, na? So this will be negative. This will be negative. Yes, negative. Now star is how much? 3 Henry. 3 Henry. D by dt of how much? D by dt of how much? 8t. D by dt of 8t. D by dt of 8t. Okay, that is understood. D by dt of 8t. Okay, na? Similarly, yes, similarly, I also need voltage in 7 because of current in 6. Now see, if current leaves the square terminal, if current leaves the square terminal of first coil, if current leaves the square terminal of first coil, then the polarity of the mutual voltage is negative at the square of the other coil. So this is again negative. Yes, minus square is how much? 1. D by dt of which current? D by dt of which current? 60. So overall this becomes, yes, minus 24 minus 6. So overall it is minus 30. It is minus 30. Okay, I will write here minus 30 volts. Now finally VAB will be, okay, VAX plus VXY plus VYB. Okay, see again, understand, sir. In first coil there is only one mutual voltage because there is no self voltage as there is no current flowing. And in the second coil there is one self and only one mutual. Though there is a coupling between 6 and 8 and 6 and 7, but 7 Henry is not excited, so only one mutual voltage. But in third coil there are two mutuals. Self is not there because current is not flowing, but both the primaries are excited, so two mutuals. Okay, na? So overall 16, 68 and minus 30. Okay, this is 16 plus 68 minus 30. So overall it is step voltage. Actually this is step voltage like DC voltage. So 38 plus 16, 54 volts is the answer. 54 volts. Okay, that is a very interesting question, sir. And answer is how much, sir? We got it as 58 volts. Now I'm giving very standard IAS objective question first. What is LXY again? What is LXY? I am taking a core on which there is a winding like this. Four Henry, 6 Henry, 5 Henry. Okay, these two are mutually coupled with 2 Henry, 3 Henry, 1 Henry. So I need total LXY. Okay, total inductance between terminals XY. Chalo, 1 minute, write some answer. Yes, everybody. Now see this question. I want total inductance between X5. See, let me consider a current of I amperes flowing like this. So in this way, it is now above and under. In this case, it is under and then above. And again, it is above and under. Okay, na? So if you apply right hand thumb rule, now see everybody right hand thumb rule here, closed fingers are current direction because current is coiled, na? Closed fingers are current direction. So if I take current above here in the first coil 4 Henry, if you take current above, the thumb shows left side. So the flux is orienting left side. So fly 1 is going left side. Okay. Now in the second coil, if you show the closed fingers as the current direction, it should go from below to above. If it is going from below to above the core, the thumb is showing right side. The thumb is showing right side. So flux phi 2 will be right side. Flux phi 2 will be right side. And finally, in the third coil 5 Henry, again, the closed fingers are the current direction. You should go from above to under. Thumb is going again left side. Thumb is left side means flux is left side. That is phi 3. So in the coil 1, flux is left side. In the coil 2, flux is right side. In the coil 3, flux is left side. Now, if you compare easily, coil 1 and coil 2 are opposing. Opposing. See, fluxes are opposing. Here, dot convention is not given, sir. But right hand thumb rule is powerful. So, here, right hand thumb rule is powerful than dot convention. Because right hand thumb rule is directly giving the flux orientation. Okay, right hand thumb rule is directly giving the flux orientation. So, in the first coil, flux is going left. Second coil, flux is going right. Third coil, flux is going left. So 1 and 2 are opposing because both are opposing. Even 2 and 3 are opposing also. Even 2 and 3 are also opposing, but 1 and 3 are aiding. So coil 1 and 2 are opposing, coil 2 and 3 are opposing, but coil 1 and 3 are aiding. So now in that regard, if I write the voltages separately, yes, V1 separately. LDI by dt self is 4, 1 and 2 opposing, minus 2, 1 and 3 aiding, plus 1. So overall 3 Henry. Okay, V2, 1 self and 2 mutual. Self is how much? 6 Henry. 1 and 2 opposing, minus 2. Yes, 2 and 3 opposing, minus 3. Okay, that is 1 Henry only. Now let us go to coil 3. In coil 3, yes, if you go to coil 3, everybody, again, self is 5 Henry, but 1 and 3 aiding, 1 and 3 aiding, plus 1, but 2 and 3 opposing, minus 3, minus 3. So this is again how much? 3 Henry. So overall, if you add, LXY will be 3 plus 1 plus 3, 7 Henry. 7 Henry is answer. Okay, 7 Henry is answer. Okay, now I'm giving another IES question. Write KVL and find natural frequency F0 of circuit. Sure. Okay. Write KVL and find natural frequency F0 of the circuit. Okay. Write KVL and find natural frequency F0 of the circuit. So write KVL and find the natural frequency F0 of the circuit. Okay. Write KVL and find the natural frequency F0 of the circuit. Chalo, sir, everybody listen. Now this is some voltage function, which is a time varying voltage function. It need not be sinusoidal. Even if it is sinusoidal, I will write, but first for any function. So it is a time varying excitation, then only everything will work. But sir, here there are two coils in series. Yes, there are two coils in series with mutually coupling. Yes, there are two coils, but he did not give dot convention. Though he did not give dot convention, but let us apply right hand thumb rule. See, this current is going here. It is going like this, and it is coming here, and it is going this way. Okay, please observe, sir. Here it is going above and under. Here also above, under, but ulta direction. Now, if you apply right hand thumb rule here, again, closed fingers are current direction. In this case, if you take current from below to above, thumb is upside. Yes, thumb is upside. So flux phi 1 is going upside. Okay, here if you show again closed fingers above to below, but left side orientation. Thumb is showing downside. Thumb is showing downside means flux is phi2 is going downside. So flux phi1 established by coil 1 because of the current direction is going upward. Flux phi2 established by coil 2 is going down. So both are opposing. These two are two coils in series opposing. Two coils in series opposing, direct formula I will write, sir. Okay, now I'm writing the KVL. Two coils in these two coils, I will write direct formula. Previously, there are three coils now, sir. So I wrote separately. But here, two coils, direct formula is there for us. So minus V of t plus IR plus L di by dt. But what is total L? L1 plus L2. Yes, minus 2m. Okay, di by dt. Okay, plus 1 by c integral I dt equal to 0. This is the general exact equation. Okay, like minus V of t, okay, plus IR plus L di by dt plus 1 by c integral I. This is a normal KVL equation. But if it is in AC steady state form, AC steady state for sinusoid, minus V phasor plus I phasor into R. Now in AC steady state reactance, plus J omega L. But what is L? Two coils in series opposing, plus J omega M, okay, plus J omega M L, the XL, okay, into I, okay, minus J, okay, by omega C into I is 0. This is also answer if AC excitation is given. But here he did not mention, sir. So I wrote first exact equation for any function. Then I wrote KVL only for AC sinusoidal excitation where all are phasors. Where all are phasors. Okay, where all are phasors. Okay, there is a meaning there. All are phasors. Okay, now he's asking resonance frequency. See, for series RLC, what is resonance frequency? 1 by 2 pi root LC. Yes or no? But here, what is L? Here, what is L? Two coils in series opposing. This is L1 plus L2 minus 2m into C. Hertz. 1 by 2 pi root L1 plus L2 minus 2m into C. That is the meaning. Okay, na? So now I am coming to gate 2 marks question. Everybody, gate 2 marks. Find power lost in 2 ohm resistor. Okay, find power lost in 2 ohm resistance. Okay, it is 50 cos 2t volts. And I gave all the circuit parameters and I want the power lost in 2 ohm. Okay, power lost in 2 ohm. Okay, I want the power lost in 2 ohms. Okay. Now this is clearly AC steady state. Everyone observe question. I'm starting now. Just observe. Yes, everybody see, I'm going with the solution now. Say I want the power lost in 2 ohms. So to find power lost in 2 ohms, I need the RMS current in it. Okay, let me write the mesh equations. Now there are 2 independent meshes. Are these meshes electrically connected? No, but magnetically coupled. So what I will try to do, chalo, I will write the mesh currents. But first, this 50 is what value? Everybody, this 50 is what value? This 50 is maximum value. This 50 is clearly maximum value. But I need the RMS current in the current I2, which is in mesh 2. Now for omega equal to 2, let me write. Chalo, for omega equal to 2, this becomes how much, sir? For omega 2, this becomes plus J4 ohms. This becomes plus J6 ohms. And this becomes minus J1 ohm. Okay. And this mutual inductance also become mutual reactance. That is plus J omega m. Omega is 2 na, plus J2. Okay, this become plus J2. Okay, na. Chalo, now I am writing the mesh currents. This is I1, this is I2. Now careful, sir. Now mesh currents. Okay, mesh 1. Now listen, sir. If I am writing the first mesh equation, yes, minus of 50 by root 2 angle 0, I am taking directly. Why 50 by root 2? Because RMS directly, na. RMS voltage I am taking means automatically currents also will be RMS, because 50 is maximum there. So 50 by root 2 is RMS, angle 0. Let it be sine or cos, sir. Now don't worry. Let it be sine or cos. Don't worry. Angle 0, because there is no phase shift, plus I1 into, first this becomes series 3 plus J4, but there is also mutual voltage in the first coil because of the current in the second coil. Na? There is also mutual voltage in the first coil because of the current in the second coil. See, here I am taking clock, here also clock. One entering, one leaving. One entering, one leaving is minus J2 into I2. Minus J2 into I2 is the first equation. Now, if I go to the mesh 2 equation, okay, if I write to the mesh 2 equation, everybody observe the mesh 2 equation also. Chalo, if I write the mesh 2 equation, here also I2 into, okay, starting from here, first plus J6 minus J1 plus 2, okay, plus J6 minus J1 plus 2. But there is also mutual voltage in this because of current in this. There is also mutual voltage in this because of current in this. Okay, mutual voltage in this because of current in this. Entering, leaving. So minus J2 into I1, minus J2 into I1 equal to 0. Now solve 1 and 2 and find I2. Okay, once you get I2, because this will be directly RMS, because I took RMS voltage, na? Then power in 2 ohms. Power in 2 ohms is this I2 RMS square into R. That many watts. That many watts. Okay, that you do later, sir. But observe, everybody, I will explain again. Observe. Okay, everybody. Okay, is it understandable here, everybody? Okay, so here actually these two meshes are independent, but they are magnetically coupled. So I wrote mesh currents, but I need RMS current into, no? So 50 by root 2 automatically RMS voltage. So RMS voltage will give automatically RMS current. So first mesh equation, minus 50 by root 2 angle 0, 3 into I1 plus J4 into I1. But there is also one mutual voltage here because of current here. Entering, leaving, minus J2 into I2. Here also second mesh equation, I2 into plus J6 minus J1 plus 2. But there is also one mutual voltage because of current in this. Entering, leaving, minus J2 into I1. Now solve these two, you find I2. That itself will be RMS magnitude. Then power is I RMS square into R. Okay, that will be the case. Okay, that is what you have to understand here. Now this is again 1 mark gate bit given for instrumentation students. What is V0? So this is 120 angle 0 volt. Okay, this is 4 ohm, J3 ohm minus J2 ohm plus J7 ohm, and this is J1 ohm. J1 ohm. And I need this voltage V0. I need voltage V0. Okay, I need voltage V0. Okay, I need voltage V0. Okay, chalo, everybody listen. I do voltage division rule. See, I will do just a simple voltage division rule, but this mutual reactance is creating a problem. First, neglect it. So first neglect this mutual inductance and mutual reactance. Now this 4 ohm, J3 ohms minus J2 and J7 become series. I can do voltage division rule. First, directly I will write. Okay, this V0. Okay, this V0 is total voltage. Total voltage is how much? 120 angle 0 into same by sum. But same, what is the same numerical point of view? Okay, the numerator, yes, same will become minus J2 plus J7 whole by sum. If I take sum, 4 plus J3 minus J2 plus J7. Okay, minus J2 plus J7. So this voltage is total voltage 120 into same by sum. Same is how much? Minus J2 plus J7 by sum. 4 plus J3 minus J2 plus J7. Okay, 4 plus J3 minus J2 plus J7. Okay, na? That we got. Yes, that we got. But here in the numerator, and denominator, what extra we have tried? The mutual effect part. Okay, I'm writing neatly again. See, if this mutual inductance concept of magnetism was not there, na sir, this total voltage into same becomes these two in series now, minus J2 plus J7 by sum means all will come 4 plus J3 minus J2 plus J7. Actually, this would be the answer. Yes, actually, this would be the answer. Yes, actually, this would be the answer if mutual inductance and mutual effect wasn't there. Okay, actually this would be the answer if mutual inductance was there. Okay, na? Yes, mutual inductance was there, wasn't there. Okay, this would be the answer if mutual effect or magnetic effect is not there. But with magnetic effect, what is extra? Now in the numerator, there will be extra one mutual voltage. Na? There will be extra one mutual voltage. Now here you see this source will drive current in the clockwise direction only. This source will drive current in the clockwise because upper plate positive, na? So this source will drive current clock. If current enters, yes, if current enters the dotted terminal of first coil, then the polarity of the mutual voltage is positive at the dotted terminal of second coil. If current enters the dotted terminal of first coil, then the polarity of the mutual voltage is positive at the dotted terminal of second coil. But this is opposite to my reference now. So this is minus J1. Plus in the denominator also, when we are writing total altogether, these two coils are series opposing. Na? These two coils are series opposing. So mutual inductance part minus 2M, you are right. Minus 2 into that mutual inductance or mutual reactance is this. So this yellow color part is extra, sir. See, the green color part would have been the answer if this magnetic concept was not there. Because all are in series, this voltage is total voltage into same by sum. But extra is what? There is one mutual voltage here. If current enters the dotted terminal of first coil, then the polarity of the mutual voltage is positive at the dotted, but negative here. This is opposite to the asked polarity. So minus J1. And in the denominator, when you write all total, these two are series opposing. Na? Series opposing means L1 plus L2 minus 2M. Na? So minus 2M will come. Minus 2M will come. Okay, that is the meaning. Okay, that is the meaning. Okay, you can simplify, sir. This V0 is 120 angle 0. The numerator become how much? It is J4. Denominator is becoming 4. J2 plus J6, I think. Yeah, 2 will cancel. That becomes 3 and J6, like that. Okay, you can simplify later, but I'm leaving here. Okay, na? That is the meaning. Okay, na? That is the meaning everyone should understand. Okay, na? Okay, sir, everybody. That is very interesting and important. Now I'm coming to another interesting question. Yes, given in gate 1 mark. Doubts at the last only, please. Doubts at the last only. Raise, put down your hand, Sangeeta. For what value of n? For what value of n Pmax occurs in the load? Okay, for what value of n Pmax occurs in the load? For what value of n Pmax occurs in the load? Now this is some supply voltage V, 45 ohms, RL equal to 5 ohms. This is n is to 1, n is to 1. Okay, chalo. For what value of n? N is the turns ratio. Okay, for what value of n maximum power is transferred to the load? Okay, for what value of n maximum power is transferred to the load? For what value of n maximum power is transferred to the load? Okay, for what value of n maximum power is transferred to the load? Sir, this is now which model of transformer? This is machine model, because L1, L2, M not there means it is machine model. Now in machine model, we know Pmax occurs in the load when load resistance is equal to source resistance. Yes, Pmax occurs in the load when load resistance is equal to source resistance, provided yes, it is a single electrical circuit. Pmax occurs in the load when load resistance is equal to source resistance, provided it is a single electrical circuit. Yes or no? But this is not single electrical circuit. How to make it single? By reflect secondary into primary. If you reflect secondary into primary, this is called R2 dash. R2 dash is R2 by K square. Okay, what is R2? 5. What is K? N2 by N1 square. N1 square. That is nothing but N square 5. N square 5. So now if you simplify this after reflection, yes, that is the meaning that you simplified by reflecting secondary to primary. You simplified by reflecting secondary into primary. Okay, this is V. This is 45 ohms. Okay, this is N square 5 ohms. Okay, N square 5 ohms. Okay, N square 5 ohms. Okay, and then for Pmax, now we can say for Pmax, load resistance is equal to source resistance. That is N square 5 equal to 45. N equal to 3. N equal to 3. N equal to 3. That is the answer. N equal to 3. Okay, na? That is the meaning. So we can say this statement: maximum power is transferred to the load when load resistance is source resistance, provided it is a single electrical circuit, sir. Provided it is a single electrical circuit. That is what is the meaning here. You have to understand that. Okay. So once this is done, yes, everybody. Once this is done, everybody. Now I'm going to another bit here. IS objective. Find current I. Find current I. Okay, find current I. This is 60 volts. This is 3 ohms, 8 ohms. This is 1:2. And I'm asking to find current I. Chalo, everybody observe the question. I'm starting the solution. Observe the question. Okay, now see this. Again, what is my idea? See, I want this current I, sir. Okay, accepted. But this is again transformer model in machines only. It is not circuit, because if it is circuit, L1, L2, M you should give. So this is machine and ideal transformer concept. So what is my idea? See, my idea is first I will find total current I total. Okay, that is delivered by the source, and by using the voltage transformation ratio, okay, I will find secondary current I. Now this current I total will be source voltage by R total now. That is nothing but source voltage by R total. But R total is R1 plus R2 dash, because these two coils are not directly connected. Primary resistance plus reflected secondary resistance is total resistance. Chalo, supply is how much? 60. R1 3. But what is R2 dash? R2 by K square. R2 by K square. 2 by 1 square this time. Okay. That is 60 by, this is 8 by 4, 2 plus 3, 5. That is 12 amperes. Yes. I total is 12 amperes. But we know voltage transformation ratio K is, okay, N2 by N1, which is I1 by I2. Sir, here I1 is I total. I2 is what is asking. So from that I is I total by 2. That is 12 by 2. Answer is 6 ampere. 6 amperes is the answer. 6 ampere, or ideal concepts are 6 amperes is the answer. Okay, na? That is the meaning here. All ideal concepts. Now this is another very interesting IES objective. Okay, what is L total? Okay, what is L total? He asked in IES. Fantastic question here. L1, L2, M, and this is short circuit. And this is short circuit. And I want L total. And I want L total. Okay, everybody see, I want L total. Now this is circuit model of transformer. See, in machine model, how we reflected, yes, we combine into single circuit by reflection. Na? Here also we combine into single circuit by reflection. But in circuit model, how to combine? T model is there. I need to bring the T model. Yes, this part, I need to write the T model. But in T model, we have two concepts. One is mutual aiding or mutual opposing. But here we are finding inductance. Inductance is what property? Inductance is passive bilateral property. Inductance is passive bilateral property. So passive bilateral properties are independent to dot convention. If question is about polarity of voltage, then we can do, sir. But here it is only to find inductance. Inductance is passive bilateral. Now that is not affected by dot convention. That was very interesting question. Everyone thought initially this is a mistake in IES, sir. See, initially everyone thought it is a mistake in IES. Okay, why? Because dot convention was not given. But actually here dot convention is not necessary, because passive bilateral properties are independent of circuit condition. So now if I do either way, a mutual aiding you do or mutual, suppose I do mutually aiding way, mutually adding or aiding way, then this T part I will write it as, yes, this T part I will write like this. Okay, this T part will be, this is plus M, here L1 minus M, and this is L2 minus M, and this is shorted. Okay, yes, secondary shorted. Similarly, if you do mutually opposing way, mutually opposing way. Okay, mutually opposing way if I do, yes, mutually opposing way if I do, this is minus M, L1 plus M, L2 plus M, and this is shorted. This is shorted. Okay, this is shorted. This is again L total. This is again L total. Okay, now if you find this L total, yes, now this L total will be this L1 minus M, then this M in parallel to this. Okay, this M in parallel to this, now there is nothing but ML2 minus M square by add, that is L2 will come here. So this is M by M, L2 by L2, this plus M minus M will cancel. So finally L total is L1 minus M square by L2. Yes, L1 minus M square by L2. Okay, now if I go to the second case, yes, second case, again this plus this in parallel to this. So this L total will be this plus L1 plus M plus this in parallel to this. That is minus ML2 minus M square by this plus this by L2 by L2. Okay, so this you remove. So again L total will be see L1 minus M square by L2. So what we have observed in both case, yes, because inductance is passive bilateral property, whether it will take aiding or opposing, answer will come same. Okay, answer will come same. Okay, observe sir. See, this was a very interesting question. Everyone thought initially that he did not give dot convention and we thought it is a mistake. But after solving it is the same. Now I'm giving gate question here. Gate question. Find V naught. Find V naught. This is Vs L1, L2. This is M, but here dot convention is given. And now he's asking voltage V naught. Very interesting, this V naught. Okay, very interesting, sir. Okay, I'm giving the options also. Vs into 1 minus L1 by M, Vs into 1 minus L2 by M, Vs into 1 minus M by L1, Vs into 1 minus M by L2. Very interesting, sir. But here, because voltage is asked, sir, that voltage, that dot conventions are mandatory. In the previous problem also, this is a circuit model of transformer. Why this is circuit model? Because self-inductance and mutual inductance is given. Previously, this is machine model because no self and mutual inductance. This is also machine model. This is okay. This is again circuit model. This is circuit model, self and mutual given. So, but this is machine model, but this is circuit model. But here inductance only was asked. When inductance only was asked, passive bilateral property, independent notation. But here is asking voltage V naught. Yes, here asking voltage V naught. So that depends upon the dot convention. Chalo, I need V naught. Chalo, sir, I give the options. Try something in 1 minute. Yes, see here now. Everybody, very interesting. I need this voltage V0, which is the voltage difference between these 2 points. Here dot convention will make sense. But if dot convention is different, then answer also will be different in this case because voltage property. Okay. So now, sir, I will write a KVL. But to write KVL, first let us find a path. But to write KVL, first let us find the mutual voltage. Now, for this given reference polarity of the supply voltage, current I1 will be clockwise now because current leaves positive terminal by a source. So current is clockwise. Now, if current enters the dotted terminal of first coil, then the polarity of the mutual voltage is positive at the dotted terminal of second coil. Then the polarity of the mutual voltage should be positive at the dotted terminal of second coil. And this voltage is how much? M di1 by dt plus M di1 by dt. So now happily I will write a KVL like this. Yes, I'm writing a KVL. Now if you write a KVL in this pink color path, minus Vs plus V0 plus M di1 by dt equal to 0. So V0 is Vs minus M di1 by dt. We got this answer. But sir, we should write the answer in given terms. This I1, etc. are your notations. But what is the Ohm's law here? What is the Ohm's law? What is the Ohm's law in coil 1? Vs is L1 di1 by dt. Yes, now substitute di1 by dt from 2 in 1. So finally V0 is Vs minus M into di1. But what is di1 by dt? Vs by L1. So V0 is Vs into 1 minus M by L1. 1 minus M by L1. This is the answer. 1 minus M by L1. So what is the correct answer? What is the correct answer? C, option C. So here there is Ohm's law, Faraday's law, and Kirchhoff's law. Okay. First, Faraday's law. Current enter the dotted terminal of first coil and the polarity of the mutual voltage is positive at the dotted terminal of second coil. That first part. Then KVL in the pink. Then Ohm's law in the first coil. All are there, sir, here. Okay. Now I'm giving another problem. This is gate. Fantastic question, 2 marks. For what value of K? See here, for what value of K the branch exhibits unity power factor, or branch, I will also write like this, branch exhibits unity power factor, or branch undergoes resonance. I will ask both ways. Both mean same because under resonance power factor is 1 now. See, under resonance power factor is 1. So for what value of K the branch exhibits unity power factor, or the branch exhibits resonance? For what value of K the branch exhibits unity power factor, or the branch undergoes resonance? For what value of K the branch exhibits unity power factor, or the branch undergoes resonance? Please understand this question. For what value of K the branch exhibits unity power factor, or the branch undergoes resonance? Okay, for what value of K the branch exhibits unity power factor, or the branch undergoes resonance? For what value of K the branch exhibits unity power factor, or the branch undergoes resonance? Okay, now see, sir. First of all, can resonance happen or not? Yes, when total net reactance is 0, resonance can happen. That means X total equal to 0. That means XL equal to XC. But what is K? K is here coefficient of coupling, please. This is our normal circuit theory. K is coefficient of coupling. So in that regard, yes, K is what? Coefficient of coupling. Now what I'm doing, yes, first of all, let us find X total, XL. XL is omega L total. That is omega into L total. These two inductors are series opposing now. That is L1 plus L2 minus 2M. Okay, because these two inductors are series opposite. That is nothing but XL equal to omega L1 plus omega L2 minus 2 omega M. But what is M? K root L1 L2. Yes or no? K root L1 L2. So XL equal to omega L1 plus omega L2 minus 2K. If you take omega inside the root, it becomes omega square. But that omega square, I will write omega L1 into omega L2. So that XL will be, now this is X1 plus X2 minus 2K root X1 into X2. X1 into X2. Now if you substitute there, now what is this XL? XL is X1, 8 plus 8 minus 2K root 8 into 8. So this XL will be 16 minus 16K, 16 minus 16K. But at unity power factor or resonance, yes, unity power factor or resonance, okay, net reactance should be 0. That means XL should be equal to XC. There is nothing but 16 minus 16K should be XC. What is capacitor reactance? 12. 12. So 16K equal to 4. So K is 1 by 4. That is K is 0.25. K is called coefficient of coupling. That means if 25% of the flux is common to both the coils, then the branch can undergo resonance. Okay, all doubts I will take up today, sir. Chalo, I am taking now 15 minutes break and we are going to start transients. Like yesterday, transients also very good introduction will give, which is very, very important, very critical. And I want everyone to please pay attention. We will take 15 minutes break. I will have a cup of tea and then we will start. Yes, transients. And all this again, I'll tell, sir, don't worry. If what all doubts you are getting in this chapter, please ask. We will go with this. Okay. Chalo, 15 minutes break for everyone. Yes, everybody. Again, welcome back. It is 11:30. 1.5 hours. I need your cooperation. So today, Pakka, I'm teaching up to 1 p.m. Everybody, please cooperate, sir. Transients, I thought I will start today by 10 o'clock. It did not happen. But I did every model in magnetic circuit. See how much I did, how many problems I did. You check it out. But still, sir, take your time. See, after syllabus is over also, we will conduct a doubt session. What do you say, everybody? Reply here. See, after syllabus is over also, we will have separate doubt session on my notes. So every problem, whatever it is, we will take that. Okay, what do you say? Okay, so that is why don't worry that Arey, sir is teaching fast. What I will do is I will separately have doubt session even after completing syllabus. In few more days, I am going to complete syllabus. I thought it is tomorrow, but maybe doubt, maybe day after tomorrow also I will continue. But once that is over, I will give some 10 days, 15 days gap, and then we will have only doubt session class. Only doubts you ask. Okay. So don't worry, sir. Even whatever partially you are understanding in my class here, there is a problem with online, sir. I am not able to see you. The clarity in explanation, all these are missing, sir. What to do? It is like myself writing question, myself explaining myself. That is what is really happening. And if I allow you to speak, sir, every individual student has their own query, and that is really creating a lot of confusion. If that was not there, sir, in offline class, sir, in offline class, everyone keeps watching and I can observe the capability of the student and I can modulate. But here it is not possible with all these things. Okay, everybody. So please understand, these are the disadvantages of online coaching. Okay, but see, everything I keep writing, that is why it is taking a lot of time, sir. Dictation not possible. Every question I am writing, every answer I am writing, every time circuit. In class, at least material is there. We can save a lot of time. That is what is really creating problem here. Okay, but anyhow, sir, my notes is everything. You read that, you will get full confidence in circuit theory. That is pakka, I can guarantee you. Okay, TK? Now, am I audible, everyone? Yes or no? Am I audible? Okay, chalo. Right. Well, let us continue further. Okay, now let us start another great chapter, that is transients. Okay, so I'm starting another chapter. Yes, electrical transients. Everybody put down your hand. Put down your hand, everybody. Everybody put down your hand. Today I'm going up to 1 p.m. Yes, 2 days you have to do work hard. Everybody put down your hand. Saumitri B. Prasad, please put down your hand. Electrical transients. Hello, sir. So this will be very important, easy and interesting chapter. Okay. Don't worry. Don't feel it is tough. It is in fact very easy, very interesting. Okay. So watch what all I am teaching very carefully. Now, first of all, what are transients? Okay. Transients are regarded as sudden change in the state of a network or circuit. First, all theory will come, sir. Theory and definitions will come. Okay. Transients are regarded as sudden change in the state of a network or circuit. Okay. Sudden change in the state of a network or circuit indicated by switch operation. Okay. Or special input function. Okay. Please understand. Okay. Transients are regarded as sudden change in the state of a network or circuit indicated by switch operation or special input function. Okay, everybody. Okay, there is a definition of transients. So what are transients? Yes, transients indicate sudden change in the state of a network or circuit indicated by switch operation or special function. That is why in this chapter all switches will come. Turning on, turning off. Okay, adding a load, removing a load, open circuit, short circuit, or I can show special function like step input, ramp input, impulse input. So all these sudden changes are transients. Okay. Now I classify transients into two types. In the first case, see the concept here. In the first case, the concept is the source is leaving the network. Okay. Okay. The source is leaving the network. So this is called as source free response. Source free response. Source free response. Example, turning off a motor. Example, turning off a motor. Turning off a motor. Okay. In the first case, what I can show? Yes, I can show that source is leaving the network. Okay. Source is leaving the network. That is turning off the network. Okay. Source is leaving, turning off. Source free response or turning off a motor. In the second case, what I can show? In the second case, what I can show? Yes, source is exciting the network. In the second case, what I can show? Source is exciting the network. Now this is called step response. Step response. Example, turning on a motor. Okay. So both are transients. See, transients are regarded as sudden change, sir. Sudden change in the state, whether it is turning off from on state or whether it is turning on from off state or turning off from on state, either way. So in the first case, what is the concept? Source is leaving the network. Switch is opening now. Switch is opening in this case. In this case, switch is opening means source is leaving. So that is called source free response, like turning off a motor. In this case, switch is closing. That means source is turning on. That is turning on a motor, like that. So both are considered as transient because sudden change in state of energy. Yes or no? That is the meaning. Then why transients occur? Yes. Transients occur in nature as well as in electrical circuits. Yes, transients occur in nature as well as in electrical circuits. Yes, please understand this. Yes, transients occur in nature as well as in electrical circuits as networks and systems. Yes, networks and systems are not adaptable as networks or systems are not adaptable for sudden changes in their energy states. Okay, transients occur in nature as well as in electrical circuits as networks and systems are not adaptable for sudden changes in their energy state. As networks and systems are not adaptable for sudden changes in their energy states. Okay, transients occur in nature as well as in electrical circuits as networks and systems are not adaptable for sudden changes in their energy state. Okay, for sudden changes in their energy state. Okay, now allowing sudden changes in their energy state. Okay, allowing sudden changes in their energy state. Okay, energy state in zero time. In zero time is not possible. In zero time is not possible. Which is violation of law of conservation of energy. Okay, which is violation of law of conservation of energy. Okay, so what I want to say is allowing sudden change in their energy state in zero time is not possible, sir. That is what you have to understand. Allowing sudden change in zero time is not possible, which is violation of law of conservation of energy. Okay, so that arguments are called transients. Okay, now specifically in electrical circuits, now I'm writing a note. Yes, in electric circuits, yes, in electric circuits, inductor will not allow sudden change in current through it. Okay, inductor will not allow sudden change in current through it. Capacitor will not allow sudden change in voltage across it. However, resistor, please understand, however, resistor can convert and dissipate. However, resistor can convert and dissipate energy in the form of heat, energy in the form of heat, can allow sudden change. Okay, please understand. So simple explanation why transients occur. So everybody listen now, I'm explaining again, everybody should pay some attention here. This introduction will be very critical and very, very important. So what introduction we are going to have today will be a very important mathematical background to start the real things. Okay, mathematical background to start the real things. Okay, so please understand that. Yes, transients are regarded as sudden change in the state of the energy. Sudden change in the state of a network or circuit. Generally switch operations or special functions also I can show. Like there are two types of transients. One is turning on process, step response. One is turning off process, source free response. Both are transients. Then transients occur in nature as well as in electrical circuits, as networks and systems are not adaptable for sudden changes in their energy state. So why transients occur means nothing in the world can change in zero time. See, allowing sudden change in their state of energy in zero time is not possible, which is violation of law of conservation of energy. Like in circuits, inductor will not allow sudden change in current and capacitor will not allow sudden change in voltage. Okay, but resistor can convert and dissipate energy in the form of heat, can allow sudden changes. Okay, can allow sudden changes. That is the meaning there. Okay, can allow sudden changes. Okay, na? That is the real meaning. Can allow sudden changes. Okay, then now I'm asking a concept question. Okay, I'm asking a question. Find I of 0 plus. Okay, I'm giving first problem here. Find I of 0 plus. What is the meaning of I of 0 plus? Current immediately after the change. Current immediately after the change. And switch is closing here. Yes, switch is closing here at t equal to 0. Switch is closing at t equal to 0. This is 2 ohm, 3 ohm, 6 ohm. Okay. Here I am giving some 20 volts. And I want this I of 0 plus. Everybody answer something. And I'm giving another question right side. Again, here also find I of 0 plus. Okay, here also find I of 0 plus. But see the change in the circuit. Everybody should observe that change. Concept is important here. Here also switch is closing at t equal to 0. This is something like 20 volts I took. 2 Henry, 3 ohm, 6 ohm. And this is the current. Chalo, in both cases, I want I of 0 plus. Just write the answer immediately, everyone. So see the difference, everybody. See here, cracker sound is coming now, sir. Can you confirm that cracker sound? Yeah, it is off now. That is why I'm not turning on. Lot of crackers here in my colony where I stay, MIG colony. That is where, sir, I was stopping actually. That is where I was stopping. Now, chalo, see this. See, in the first case, pure resistor network. In the second case, there is an inductor also. Now, sir, here I told that, now, sir, resistors can allow sudden change by immediately converting and dissipating energy in the form of heat. So I will write like this. First of all, here, what is I of 0 minus? Okay, what is the meaning of I of 0 minus? I of 0 means previous steady state. Previous steady state switch was open, so current is 0. Okay, but what is I of 0 plus? The moment you turn on, immediately resistors can convert, so they can allow sudden change. So 20 by okay, 2 plus 3 in parallel to 6, so 20 by 4, it is 5 amperes. So answer is 5 amperes. Then what is I of infinity steady state? Yes, once current immediately reaches 5 amperes, it will stay there forever. So that is final also 5 amperes. Okay, so finally the answer is how much, sir? The answer is 5 amperes. But you see the right side. You see the right side. Here also I of 0 minus is 0 because switch was open, current cannot flow. But I of 0 plus is also 0 here. Now this is very interesting because inductor will not allow. Inductor will not allow. Yes, sudden change in current. Allow sudden change in current. Sudden change in current. That is a concept here. Inductor will not allow sudden change in current. Okay, that is why here answer is 0. Here answer is 0. Okay, but what is I of infinity in this case? Now see, DC steady state infinity, inductor acts like short, na? That is 20 by inductor short, that is 3 in parallel to 6, 2, 20 by 2, that is 10 amperes. So see the difference in both the cases, sir. See, first only resistors are there, then current can immediately reach. Current can immediately reach because resistors are not violating law of conservation of energy. No element will violate, but the difference is resistors can immediately convert and dissipate. 20 by 4, 5 amperes. And I of infinity is also 5. But here inductor will not allow sudden change in current. Na? So I of 0 minus is 0, but I of 0 plus is also 0 because inductor will not allow immediate sudden change in current in 0 time. That is a big difference. So here I of 0 plus is 5, but here I of 0 plus is 0. Please understand the difference. Here I of 0 plus is 5, but here I of 0 plus is 0. That is a big difference. Understood, sir? That is very interesting. Okay. That is what you have to understand. The difference with inductor. Inductor will not allow sudden change in current through it. Okay. That is a big difference you have to show. Now I'm further continuing. Transients are regarded as an argument. Okay. Transients are regarded as an argument between input excitation to output response. Yes, transients are regarded as an argument between input excitation and output response as network reaches its next steady state from the previous steady state. Okay, transients are regarded as an argument between input excitation and output response as a network reaches its next steady state from the previous steady state. Okay, though transients occur for very short duration in time. Yes, though transients occur for very short duration in time, but their analysis is very critical. Yes, but their analysis is very critical as this state can determine and affect, okay, determine the overall steady state stability in the network. So though transients occur for very short duration in time, but their analysis is very critical as this state can determine the overall steady state stability in the network. As this state can determine the overall steady state stability in the network. Now, customers of electrical network applications look into its steady state performance. Yes or no? That is why DC and AC steady state we learned. Okay, customers of electrical networks look into steady state performance, but a designer is always interested. Okay, but a designer is always interested in its transient behavior, transient state behavior. Okay, transient state behavior as the critical design parameter values are evaluated. Okay, why? See, customers always want steady state performance, but a designer is always interested in transient state behavior as this state can determine, transient state can determine, the critical design parameter values. Okay, again read this. I'm going to explain now. What does it mean? Transients are sudden changes. They are like arguments between previous steady state to next steady state. That is why the dynamic, linear circuit, but non-linear behavior we call. And though transients are for short time, but they are devastating, sir. Okay, sudden rate of change in current, sudden voltage fluctuations, all these are transients. Fault analysis in power system, power electronic concepts, okay, open circuit faults, short circuit faults, motor starting, motor braking, all these are transient, and that is where more stress is there in the electric circuit. So overall transients are short time compared to steady state, but they are devastating. So that is why we should be very careful. Then customer always looks into steady state performance, but designer is always focused on which state? Transient state, because that state only will give the secrets. Okay, the design parameter values. Okay, now sir, state variables. Now listen here, state variables. Okay, state variables. Okay, these are the critical parameters. Okay, these are the critical parameters that should be observed, okay, these are the critical parameters that should be observed in any network, which can determine the correct state, at any instant in time. Okay, These are critical parameters that should be observed in any network. These are critical parameters that should be observed in any network. Okay, these are critical parameters that should be observed in any network, which can determine its correct state at any instant in time. Okay, what are they especially? Yes, in inductor. First, I will write in a capacitor. In a capacitor. Okay, since in a capacitor, since I is C dV by dt. Yes, in a capacitor, since I is C dV by dt. Okay, yes, voltage across. Yes, voltage across capacitor. Voltage across capacitor is correct state variable. Okay, in a capacitor, since I is C dV by dt, voltage across capacitor is correct state variable. Okay, but to get this, I will write KCL, that is nodal equation as preferred. Why nodal equation? Because I is C dV by dt, so I should write KCL. So whenever RC circuits come, remember nodal equations you write, then the differential equation will come. Because in a capacitor, I is C dV by dt, the rate of change of voltage will tell everything. That is why voltage across capacitor is state variable. Suppose voltage is positive rising, it is charging. Voltage is negative falling, it is discharging. Voltage is constant, then dV by dt is zero, na? Steady state. Like that we can argue. So in a capacitor, voltage across capacitor is correct state variable. To get that, I need to write what? KCL, nodal equations. Then in an inductor, yes, in an inductor, since V is L di by dt, that is the differential equation we get. Okay, since V is L di by dt, yes, I say the current through inductor. Current through inductor. Yes, current through inductor is correct state variable. Is correct state variable. But to get this, I need to write KVL, that is mesh equation. Okay, to get this, I need to write KVL, that is a mesh equation. Okay, to get this, I need to write KVL, that is a mesh equation. Okay, now that is the meaning. So these are the meaning of state variable. Everyone read again. Okay, so meaning of state variable we understood here. Okay, now if I further continue, now this is the most important paragraph. Okay, I want everyone to follow this paragraph. Any circuit or network, any circuit or network will have two types of responses. Will have two types of responses. Two types of responses. Okay, any circuit or network will have two types of responses. In that Roman letter 1. Roman letter 1. Yes. The response of a circuit or network. The response of a circuit or network. Okay, the response of a circuit or network with source present in it. With source present in it. Okay, the response of a circuit or network with source present in it is called as forced response. Okay, is called as forced response. Okay, which leads to steady state response. Okay, the response of a circuit or network the response of a circuit or network with source present in it is called as forced response, which leads to steady state response. Okay, which leads to steady state response. This response, okay, is independent. This response is independent to nature of passive elements. Okay, this response is independent to the nature of passive elements, but purely depends upon the type of input. Yes, but depends upon the type of input. Okay, this response can be different for different types of input, for different types of input. Okay, example, I will write here, example, DC and AC. Yes, DC and AC steady state responses. Okay, DC and AC steady state responses. Okay, DC and AC steady state responses. Now I'll write a note that the solution to this part of differential equation okay, the solution to this part of differential equation, please understand the meaning. The solution to this part of differential equation can be obtained. Yes, the solution to this part of differential equation can be obtained by solving the particular integral part of it. Okay, the solution to this part of differential equation can be obtained by solving the particular integral part. Okay, the solution to this part of differential equation can be obtained by solving the particular integral part. Please read this. I am going to explain now. Okay, everybody, see, the response of a circuit or network with source present in it is called as forced response. That leads to steady state response. This response is independent of the nature of passive elements, but purely depends upon the type of input. This response can be different for different types of inputs like DC steady state, inductor short, capacitor open, resistor is normal, AC steady state, inductor is lagging, capacitor is leading, again resistor is homogeneous normal, like that. And the solution to this part of differential equation can be obtained by solving the particular integral part. Okay, particular integral part. Okay, that is the meaning. By solving what? Particular integral part. That is very important to understand. Okay, na particular integral part. Then Roman letter 2. I am going to Roman letter 2. Now the response of a circuit or network without any source in it, is called as natural response. Okay, is called as natural response, which leads to transient state behavior, transient state response. Okay, the response of a circuit or network without any source. Now you may say, sir, how can circuit work without source? Circuits work without source because of their initial condition, stored energy. The response of a circuit or network without any source in it is called as natural response, which leads to transient state response. This response is independent to the type of input. Okay, type of input, but purely depends upon the nature of passive elements. Okay, the response is independent to the type of input. Yes, this response is independent of the type of input, but purely depends upon the nature of passive elements. Okay, but purely depends upon the nature of passive elements. Okay, this response is always unique. This response is always unique. Which can be determined. Yes, which can be determined. Okay, determined by solving the characteristic equation by solving the characteristic equation governing the network. Okay, this response is always unique, which can be determined by solving the characteristic equation governing the network. Okay, by solving the characteristic equation governing the network. Like here, example, source-free responses. Okay, source-free responses. Okay, I'm writing a note again. The solution. Yes, the solution to this part of differential equation. Can be obtained by solving the complementary function part. The solution to this part of differential equation can be obtained by solving the complementary function part. Okay, the solution to this part of differential equation can be obtained by solving the complementary function part. Okay, the solution to this part of differential equation can be obtained by solving the complementary function part. Okay, that is very, very important. Now, how can circuits respond even without source? Yes, how can circuit respond even without source? I am writing the note here. Okay, I'm writing the note. Okay, circuits and networks can respond. Okay, circuits and networks can respond even without source. Okay, circuits and networks can respond even without source provided, okay, circuits and networks can respond even without source, provided they have some initial stored energy. Okay, circuits and networks can respond even without source, provided they have some initial stored energy. Like again, in a capacitor, what is that? Q equal to CV. What does it means? This is the Ohm's law now. Q equal to CV. That means, yes, internal stored electrostatic energy. Yes, internal stored electrostatic energy will give rise to initial voltage. Yes, initial voltage, and that can drive the network without source. Similarly, in an inductor, psi is Li. Okay, here again, internal stored electromagnetic energy can give rise to initial current. Okay, yes, internal stored electrostatic energy give rise to initial voltage, and internal stored electromagnetic energy can give rise to initial current. Okay, that is how. See how circuits can respond even without source. That is a reason. Now, if I combine this, yes, case 1 and case 2. Now I'm writing everything. So total response. Total response of a circuit. Okay, total response of a circuit is equal to forced response. Yes, forced response plus natural response. Okay, forced response plus natural response. Now this forced response leads to steady state. This natural response leads to transients. Okay, natural response. And technically this is called as zero state response. That means no initial condition. No initial condition is required in calculating steady state. Yes or no? We did DC and AC steady state. Initial condition was never required. If it is there, we take, otherwise no need. But this is called zero input response. Zero input response. That is why I write here total solution to differential equations, yes, is equal to particular integral plus complementary function. Particular integral plus complementary function. Okay, that is why here in this chapter example answers look like, okay, like V of t is equal to some 5 plus 3 e power minus 2t volt, like that. Suppose some current in AC transient also, some 10 cos 2t plus e power minus 2t, okay, sine 3t. Okay, I can show like this. Okay, even overdamped I can show. Suppose overdamped case example I'm telling. Okay, some 4 e power minus 2t minus 2 e power minus t. Okay, amps, like that. Okay, all mathematics, at least listen whatever I'm saying, read. That will be saving a lot of time for us tomorrow. Okay, that is necessary for me, necessary here. So I will explain all this again. Very, very important. Everyone observe now. Read the second paragraph first. Yes, everybody see now. See, so first statement I told everyone, but what is second statement? See, the response without any source is called natural response or transients, which leads to transient. But how can the circuit work without source? This is the reason. Without source, the circuit can work provided initial conditions exist. Either capacitor has initial voltage or inductor has initial current. That will give the concept of source free. That is, during turn off, those energies are responsible. But this response is always unique and leads to transients. Okay, and the solution is complementary function. That is why here total response is forced plus natural. Forced response leads to steady state. That is why here steady state means here t tends to infinity, like DC steady state, AC steady state. Transients means t tends to 0 plus sudden change, that concept. So we already completed steady state now, sir. DC steady state, AC steady state, but transient part we missed out. Now steady state is called zero state response, independent to initial condition, but natural response is called zero input response. Okay, that is why in this chapter answer look like 5 plus 3 e power minus 2t, 10 cos 2t. Okay, 10 cos 2t plus 4 e power minus 2t, like that. What is the meaning? Steady state value we know how to find. If it is DC input, DC steady state will come. If it is AC input, AC steady state will come. But this natural part we missed out. Yes, we missed out the natural part. Okay, that we need to find. Now let us understand what is the order of a circuit. Order of a circuit or network. Circuit or network. What is order of a circuit or network? Okay, the number of, yes, the number of energy storage elements, the number of energy storage elements. Yes, the number of energy storage elements. Okay, available in distributed form but interacting. Distributed form but interacting. Okay, the number of energy storage elements available in distributed form but interacting represents the order of a network. Order of a network. Please read this. The number of energy storage elements available in distributed form but interacting represents the order of a network. Like example, like RL circuit, RC circuit is first order. Okay, and this RLC, double LR, double CR, pure LC tank circuits are second order. Okay, RL, RCR first order, RLC, double LR, double CR, LCR second order. Okay, these are second order. Now that is why I'm writing a question here. Okay, find the order of network. Find the order of network. Okay, I'm giving here, find the order of the network. Which is moving from A to B. Vs R1, R2, R3, C1, C2, C3. Okay. Now everybody, what is the order? See, you may say, sir, there are three capacitors. It is third order. No, sir. No, sir. Though there are three capacitors, everybody please listen. Though there are three capacitors, we can lump all capacitors into single capacitor now. Though there are three capacitors, we can lump all capacitors into single capacitor. Please understand this. Yes, though there are three capacitors, please understand, we can lump all the capacitors into single capacitor. So this becomes first order only. We can lump all together into C total. C total. So this is first order only. In case if you cannot lump them, then it is higher order, which I will tell you later. Okay. So though there are three capacitors, don't say it is third order. As long as you can lump into single element, yes, it is first order only. So the order of circuit is the number of energy storage elements available in distributed form. Here lumped form, I can simplify into single element. But if it is distributed and you cannot lump, then here what is the reason? This C2 and C3 are parallel. So C2 plus C3 and in series to C1. That is why it is first order only. Okay, na? Remember, first order only. Okay. Then what are initial conditions? Yes, initial conditions. What is the meaning of initial conditions? Okay, these are the critical values. These are the critical values of, okay, voltage across capacitor, and current through inductor, These are critical values of voltages across capacitor and currents through inductors. Okay, these are the critical values of voltages across capacitors and current through inductors that must be considered from the previous steady state. Okay. Okay, these are the critical values of voltages across capacitors and current through inductors that must be considered from the previous steady state so as to determine the solution to its next steady state. Okay, now initial conditions. These are the critical values of voltages across capacitors and current through inductors. Yes, these are the critical values of voltages across capacitors and current through inductors that must be considered from the previous steady state. So as to determine the solution to its next steady state. Okay, that must be considered from the previous steady state so as to determine the solution to its next steady state. Okay, now that is what, sir, these are the memory elements now. Which are memory elements in my subject? Capacitor and inductor. And what are the memory values? Yes, memory values are inductor current and capacitor voltage. Yes or no? Memory values are nothing but inductor current and capacitor voltage. So what are initial conditions? These are the critical values of voltages across capacitors and current through inductors that must be considered from the previous steady state so as to determine the solution to its next steady state. Yes or no? That is the meaning. Now, these are indicated in time. Okay, these are indicated in time as follow. Okay, what is the meaning? Like t equal to 0 minus. T equal to 0 minus means, yes, instant just before transient, okay, transient, or just before switch operation. I will write like this: switch operation. Okay, this is previous steady state. I can say this is previous steady state where initial conditions come. Okay, this is where initial conditions come. Initial conditions will come. Okay, initial conditions will come. Okay, so these are the critical. What are initial conditions? These are the critical values of voltages across capacitors and current through inductors that must be considered from the previous steady state so as to determine the solution to its next steady state. So previous steady state is where before switch operation. That is like we write t equal to 0 minus. Okay, what is the meaning of t equal to 0 minus? T equal to 0 minus is instant just before switch operation. Yes, instant just before switch operation. That is previous steady state. Okay, previous steady state. Okay, that is the meaning there. Okay, previous steady state, that is instant just before switch operation. Okay, then I'm just writing extra points here. Okay, then I'm writing these extra points here. Okay, what is the meaning of t equal to 0? Okay, what is the meaning of t equal to 0? Okay, t equal to 0 means exact instant. Okay, exact instant of switch operation. Exact instant of switch operation. Okay, this exact instant of switch operation. Okay, this is exact instant of switch operation. Okay, that is transient state. Okay, this nothing. Okay, of course in zero time nothing can be changing now. That is nothing can be done. Okay, zero means exact instant, nothing can be done because nothing in the world can change suddenly. But t equal to 0 plus, this is important. This is important. Instant just after switch operation. Just after switch operation. Instant just after switch operation. Switch operation. Okay, instant just after switch operation. That is the transient state. This is the transient state. Transient state. That is a transient state. Okay, that is a transient state. Okay, then finally t tends to infinity. What is the meaning of t tends to infinity? Yes, steady state after switch operation. After switch operation. Okay, so that is what everyone please understand. Zero minus means previous steady state. Instant just before switch operation, that is previous steady state. That is where initial conditions come from. T equal to 0 exact instant, nothing can be done because nothing in the world will change suddenly in zero time. But t equal to 0 plus is instant just after switch operation, that is called transient state. And t tends to infinity, steady state. See, that is how in this chapter we do analysis from previous steady state to next steady state. We do analysis from previous steady state to next steady state. In all the previous chapters, we directly went to steady state. In all the previous chapter, we directly went to t tends to infinity. But in this chapter, we are starting from 0 minus initial conditions, and then we are going to transient state and then go to final value. That is why this is a solution on dynamic behavior of the networks. So that is why we call dynamic behavior. So dynamic solution, dynamic behavior of networks. Why it is called dynamic behavior? We are starting solution from previous state, that is 0 minus, where initial conditions come, to transient state and then final value. Okay, that is the meaning. But however, initial conditions come from which state? 0 minus. So here I'm writing a note. However, we know that yes, VC of 0 minus is VC of 0 plus. Why? Because capacitor will not allow sudden change in voltage, and IL of 0 minus is IL of 0, which is also equal to IL of 0 plus. Here also I will write like this. Okay. Here also I will write IL of 0. Yes, here I will write VC of 0. Okay. VC of 0, which is VC of 0 plus. Why? Because here capacitor will not allow sudden change in voltage. Here inductor will not allow sudden change in current. That is why, yes, that is understood. So in capacitor will not allow sudden change in voltage. So this is a valid statement. Okay. Inductor also will not allow sudden change in current. This is a valid statement. Okay. That is what you have to understand. Okay. That is what you have to understand. Okay. Now a very important paragraph. Behavior. Listen carefully. Behavior of passive elements. Behavior of passive elements in transient state. Transient state. This is very, very, very important, sir. So in every chapter like DC steady state, we understood. AC steady state also first day, phasor, J operator, like that. Here also, how elements are behaving in transient state is required for me first. Okay. How elements are behaving for transient state, first we should know. Then only we can understand this chapter. And that to mathematics is then, sir, mathematically we have to learn. Okay. So behavior of passive elements in transient state. So we are learning that first. Okay. Behavior of passive elements in transient state. That is very, very essential for us. Okay. Now, let us learn that. What is the meaning of behavior of passive elements in transient state? Now here I'm writing. Yes, here I'm writing. If analyzing, okay, a circuits, okay, for sudden changes, if analyzing circuits for sudden changes in time, okay, that is t tends to 0 plus, that is t tends to 0 plus is considered as transients, okay. If analyzing circuits for sudden changes in time, t tends to 0 plus is considered as transients. Okay. Then analyzing the same circuit, then analyzing the same circuit, okay, as S tends to infinity, because time and frequency are inversely proportional. Time and frequency are inversely proportional. T tends to 0 means S tends to infinity. But what is S tends to infinity? Steady state frequency solution. So analyzing circuits for sudden changes in time, that is T tends to 0 plus, is considered as transients. Then analyzing the same circuit as S tends to infinity, okay, S tends to infinity, which is steady state frequency solution, which is steady state frequency solution, okay, which is steady state frequency solution, will also include, okay, will also include, yes, will also include, okay, will also include the transient part in it, the transient part in it, transient part in it. Hence Laplace transforms are powerful tools to analyze circuits during transients. Hence, Laplace transforms are powerful tools to analyze circuits during transients. Hence, Laplace transforms are powerful tools to analyze circuits during transients. Okay, please understand. Read this statement again. I will tell you the meaning. Everybody read this. Yes, everyone. We'll conclude in few minutes, sir. But listen, very important conclusion. Behavior of passive elements in transient state. If analysis of circuits for sudden changes in time, that is T tends to 0 plus, is considered as transients, then analyzing the same circuit as S tends to infinity. See, time and frequency are inversely proportional. T tends to 0 means S tends to infinity. But S tends to infinity means steady state frequency solution. So analyzing in time domain 0 plus is more difficult than analyzing circuits as S tends to infinity steady state frequency solution. Hence, Laplace transforms are powerful tools in analyzing circuits during transients. Okay, that is why Laplace is coming here. That is very, very interesting. Okay, now see, this table is important here. Element. Okay, element, first time writing. Okay, that is we know R, L, C. Okay, behavior in. Okay, now we know the element represented in frequency domain. Okay, element representation. Okay, representation. Okay, I'll write here. Let me write, sir, because space is very important for me. I will write here neatly. Okay, first element. Okay, one is R, L, C. Okay, and element represented in frequency domain. Okay, representation of element in frequency domain, for any signal. Okay, representation of element in S domain or frequency domain. Frequency domain where S is equal to j omega for any frequency. That is the meaning we are calling. Okay, that I will tell you now. Then we know the three parts, steady state and transient part we know. Yes, we know the steady state part and transient part. Now behavior in DC steady state we already completed. Behavior in AC steady state also we know. Now behavior in transient state. We are learning this. Okay, we are learning this. Okay, so representation of element in frequency domain. S is equal to j omega. Okay, so representation of element in frequency domain, that is S is equal to j omega. These are all mathematics. Okay, this is all mathematics we are learning here. Mathematical way we are learning. Okay. Now this is element RLC, representation of element in frequency domain. S is equal to j omega, na sir? Yes, S is equal to j omega, complex frequencies. Now first register is independent of frequency, R is R only. But what is impedance of inductor? You know, it is plus j omega L. Now j omega is S na, so this become SL ohms. R is R only. But capacitor, we know impedance of capacitor is 1 by j omega C. You remember this, right? XC we used to write. But j omega is S na, 1 by SC ohms. So what is the difference in AC and this chapter? In AC circuit analysis, it is a sinusoidal input for constant frequency omega. Yes or no? In AC circuit analysis, it is sinusoidal input for constant frequency of omega. But here we are doing analysis for any input at any frequency where S is equal to j omega. Understand the difference? We can give now any input at any frequency where S is equal to j omega. Then how to represent elements? It seems R is R, L is SL ohms, C is 1 by CS ohms. Now, you know, DC circuit analysis means what? Zero frequency. Omega 0, S is 0. AC circuit analysis means S is equal to j omega, where omega is constant. Omega is fixed, constant. Okay. But transients means T tends to 0 plus. But what is the meaning? T tends to 0 plus means S tends to infinity. Na? S tends to infinity. That is important. Transients means S tends to infinity. So now based on this, chalo sir, conclusion. R is R because R is independent of frequency. In DC also same, AC also same, transient also same. What is the meaning of transient also same? That means register is independent of frequency. Whatever sudden input you give, sudden output will come. Sudden step voltage, sudden step current. Sudden impulse voltage, sudden impulse current. So register is not a problem because it has the ability to convert and dissipate energy in the form of heat. It has got the ability to convert and dissipate energy in the form of heat. So register is not an issue, sir. Okay, register is really not an issue. Okay, that is why register is easy to understand. But what about inductor? Inductor. Yes, inductor for DC steady state, because S is 0, you put 0, impedance is 0. So inductor acts like short circuit in DC steady state. But in AC steady state, S is equal to plus JS, that is plus J omega, na? That is plus J XL omega L. So I will say here IL lags, okay, IL lags VL by exactly phase how much? 90 degrees. And now in transient state, this is interesting, sir. In transient state, how inductor is behaving? Listen now. In transient state, T tends to 0 means S tends to infinity. S tends to infinity means impedance is also infinity. Impedance also infinity means inductor acts as open circuit. Just after change, inductor acts like open circuit. That is very interesting behavior. See this conclusion. Similarly, capacitor. If I go to capacitor, yes, again capacitor. For DC steady state, S is equal to 0. Something by 0 is infinity, na? Infinity. So capacitor acts as open circuit for DC. Okay, capacitor acts as open circuit for DC. Then for AC steady state, if you go with AC steady state, yes, here IC leads VC by 90. And in transient state, if you observe, yes, in transient state, if you observe, yes, T tends to 0 is S tends to infinity. Something by infinity is 0, na? Yes, it acts like short circuit. Okay, it acts like short circuit. Okay, so this table is the most important table, and in that the last column is our transient. The last column is our transient. That is extra we are learning. 0 plus is different, sir. 0 plus is different. Okay, this is how equivalent circuit representation of passive elements in transient state. Okay, that is how we call this as equivalent circuit representation of passive elements in which state? Transient state we are learning. Okay. Yes, we completed everything today. We will stop here. Okay, all these notes I will give you. Please read and come tomorrow. Otherwise, you will not enjoy the class tomorrow. Tomorrow will be the major chapter called transient. But this introduction, see all this theory, what we learned since last 1 hour. See, all this theory will be helpful tomorrow. Okay, what is transient? What are the two types of transient? Step response source free. Why transients occur? And which elements are causing transients in circuit? What is the meaning of 0 plus here, 0 plus there? Okay, why transients are so important? Then state variable means what? Two types of responses we learned, and total response we represent. Okay, why the solution will be like this mathematically we are learning. Then order of a circuit, initial conditions. Okay, then behavior of passive elements in Laplace domain. So that is very important, sir. Okay, tomorrow however I will brief and we will go for doubts now. Chalo, take your time to learn and ask doubts tomorrow also. Okay, Bimilendu, what is your doubt?
Sir, in the last page that you hello.
Bimilendu, I am unable to listen to you. Wait, I'm
Hello.
Bimilendu, please again can you ask, because there is a problem in my mic. Okay, tell me Bimilendu, what is
Okay. Okay, that's our behavior in the passive element. We are in the last page, sir.
this only? Yeah.
Yes, sir. The behavior passive element. I am exciting with the sinusoidal input for a resistive, purely resistive network.
Okay.
Okay.
Then
Then the steady state I can't achieve, means S tends to infinity. I can't say that the transient behavior is that much.
Transient won't occur. See, suppose even in register, suppose sinusoid with pure register you take. The instant when you are closing the switch, same output will come, like you are running
Yes,
power
sir.
electronics now. Whenever you switch current, current also will be same.
Means can we say here Laplace transform is not following, means S tends to infinity, means output is sinusoidal for sinusoidal.
S tends to infinity here means S tends to infinity means steady state after few cycles. Steady state after few cycles. That will be the same as input. That will be same as input. See, once you close the switch here, yes, it is understood that you are getting the same here. After from here, now, sir, it will follow the supply only.
Okay.
Okay, that means same.
Means but for S tends to infinity, we can't say that S tends to infinity we can put for a purely resistive network like inductor and capacitor. We can put because they
we can put that impulse is the same response we get.
But sir, in a signal system we already learned that in a S tends to infinity only for a sinusoidal input we can't put S tends to infinity.
No, here the data here is that is ideal impulse concept they are teaching. That is why T tends to 0. That is all mathematical only. But meaning here is, see, S tends to infinity meaning is S tends to infinity is a concept that it is called steady state frequency solution. In that steady state frequency, see what is T tends to infinity solution? T tends to infinity solution means steady state time domain solution.
Yes, sir.
Here S tends to infinity solution means steady state frequency domain solution. But I'm not arguing it is that we are doing analysis at S tends to infinity or S tends to 0, something like that. Okay.
And sir, another doubt is that passive and bilateral. That inductor where passive means that positive input and positive current will be inside.
That is understood. But bilateral is important for property. Bilateral elements behavior is independent to circuit condition.
Okay, bilateral means
whether dots are there or not there, mutually aiding or mutually opposing, bilateral elements behavior is independent to circuit condition. Okay. So because we are asking inductance there, which is bilateral property, so that dot convention has no effect. But where second problem again, where voltage was asked, then dot convention is mandatory.
Okay, means that problem only bilateral is the major problem.
Anywhere where you are finding only resistance, inductance, capacitance, then dot convention will not affect. That is the meaning. Okay. Right. Imtiaz.
Good afternoon, sir.
Tell me, Imtiaz.
Sir, in last question, means in the magnetic circuit.
Okay. Tell
there
me.
are 4 options. Vs 1 minus L1 by N.
Yes, I understood. Tell me.
Sir, in that we can transfer as the circuit model, no, sir. L1 minus M.
See, if you are writing into T model, na, sir, But until and unless you consider this positive notation, because dot is there na, that dots will create a confusion, because secondary side current is not flowing na, open circuit
yes,
na,
sir.
we cannot directly consider whether it is mutual aiding or opposing. That confusion generally comes.
Sir, from that I got means the right side part is open circuit. No, there is no current flow. That's why I'm thinking that there's voltage division rule between the L1 minus M and plus M.
Yes, L1 minus M and plus M should be.
Voltage division rule. With the help of voltage division, we can find at the point of L1 minus M voltage.
Yes, you can find.
I got same answer with that, sir.
But the thing is, how can you justify here mutually aiding only? Mutually opposing ulta.
But they are given no, sir, that dot convention.
But what is my argument here is dot convention here is only telling the polarity of the mutual voltage. But actually here the problem comes in T model, how to represent directly as aiding or opposing. That is the confusion I'm getting. Understood my doubt, huh?
Yes, sir.
In T model.
Sir, one more, sir. Okay, I got that point. In the options, there is no plus point.
That way, yeah. Option wise, you can argue. But if plus is given, then that argument fails. Correct.
Okay,
Based on
sir.
option and your concept, it may match. But suppose, yes, if I put plus, then the problem will come. Yes or no?
Yes, sir. Means there
That is
is no confusion in the option.
That is why here, when compared to this problem, why I did not entertain dot convention is we don't know here whether to take mutual aiding or opposing, especially we are finding voltage here. But here, confident it is a passive notation, that doesn't matter.
Okay, sir.
Okay.
I got it.
Right.
Sir, one more, sir. In yesterday problem,
Ah.
sir, we are in that we have two coils of the practical coils R1 L1 and R2 L2 is there, no, sir, for
Okay.
finding of the quality factor.
Yes, tell me.
Sir, from before that you gave one point as the Genco bit QL is equal to 1 by Q1 plus 1 by Q2. With the help of that formula, I'm not get the answer.
Why? Because that one inductor and one capacitor is compulsory. Yes, your doubt. Yes, very good. I'm coming there. Wait. See, this formula is applicable. Only if there is one inductor and one capacitor, not both inductors or both capacitors. This formula. See, this formula is combined quality factor of a practical inductor and practical capacitor.
Okay, means,
but here both are inductors. Here both are inductors, not valid.
Okay, sir.
So this formula is valid. One is inductor and one is capacitor. Then it is correct.
Okay, sir.
Okay.
One more, sir.
Sir,
we are discussing at the first order, second order. What do you mean of the third order, sir?
It is there. Third order also there. But see, why only second order? Because the dominant poles will conclude everything. Why even control system we are learning second order enclosing? Because by second order itself, we will know the overall behavior of the system. But third order, fourth order, higher order, also there. But we study mathematically up to second order and conclude overall stability. There is enough for us for accuracy in mathematics. But if you want more accurate solution in design level, they take third order, fourth order also. 100% we take. That is why state variable is coming now. See, state variable analysis is for any order.
Yes, sir.
Memo input, multi-input, multi-output. But time domain solution up to second order is enough to tell the stability of the network.
Okay, sir.
State variable came for higher order only.
Sir, one more, sir. Sir, in the matrix form, we are getting the 5 minus 3, 1, 3 minus 5 there, sir.
Yeah.
Is the symmetry matrix always no, sir?
Yes, 100% it will be symmetry because M12 equal to M21 in my case.
Not only in this, all problems.
All problems, even in power system. See, that is why you see our power system Y bus, Z bus will be symmetrical.
Yes, sir.
Because there in transmission line mutual inductance and that transmission line also same will come.
Sir, if we did any means mistake in the exam, so with the help of symmetric, we can conclude.
We can tell. Even that same things exist in topology. Topology, unfortunately, has been removed in GATE and IS. These days, I am not teaching. But in topology, also such matrices I will write and show everywhere it is symmetry. Canonical form P inverse AP will come everywhere.
Yeah, okay, sir.
Okay. Yes.
Sir,
correct.
one more, sir. Last minutes. In that, DC steady state means P of 0 minus 1, sir. For both.
DC steady state means T tends to infinity for DC input.
This, sir, when we take the T is equal to 0 minus.
0 minus means previous steady state. Like switch off means current is 0. See, in the example problem where I started this discussion, see, register will allow sudden change. That is a different issue. But steady state means always go to T tends to infinity. Steady state means always go to T tends to infinity. Here you see steady state means always at infinity. Always remember that. 0 minus means previous steady state where initial conditions come.
Whatever may be initial.
This 0 plus is what we are doing in this chapter that we missed out. That means in all the previous chapter, if it is DC input, DC steady state we did. If it is AC input, AC steady state we did. But in this chapter, we are learning where in is starting initial condition and how the response is going under lambda, over lambda, critical lambda. All this we are learning in 0 plus state.
Okay.
Okay.
Yes,
Yes.
sir. All right. Thank you so much.
Yes, right. So tomorrow again, everybody 7 o'clock to 1 o'clock. Tomorrow again will be very important day for transient. So don't miss out. Okay, Navdeep, what is your doubt?
Hello?
Tell me, Navdeep.
Sir, in series resonance and parallel resonance, we are actually placing the resistance, or it is resistance of inductance and capacitance, sir?
Their resistance actually models the resistance of these passive elements where losses are modeled. But purposefully in design, no one will put resistance. Their resistance is purposefully modeling the losses of LNC elements only, which decides the quality factor.
Okay, sir.
R is not put in the design. R is there to model the losses of LNC.
Okay, sir.
Okay, right, correct.
Hello, sir.
Tell me.
Sir, last word. Sir, in the transformer model, we are taking K is equals to N2 by N1. Here, that is one problem. 1:2 ratio. Then can I say that in the higher side resistance is increasing? So I can take that is.
Yeah, we learn in transformers. That is true, na. In transformers, that is really true.
Okay.
Yes,
But
absolutely.
when ratio is given n is to 1, then it is confusing. Means which will be
Always remember.
N1
See, always remember. See, that is why, sir, there is a really, even today, some books give different way. See, general turns ratio. General turns ratio means N1 by N2.
N2.
Ah,
According to that,
voltage transformation ratio or transformer ratio means N2 by N1.
Okay.
That is why to remove that is why to remove confusion. See, some now good books are writing like this. Now to remove all this confusion, they are writing like this. Okay, K means voltage transformation ratio or transformer ratio. That is always N2 by N1.
Yeah.
But in some foreign books now they are writing primary turns ratio, secondary turns ratio. Primary turns ratio they are taking N1 by N2. Secondary turns ratio means N2 by N1. There also.
Means if in one problem it is given from the secondary side, it will be exciting. Means we can take the primary side as a N2.
Primary side. No need. Primary always take N1, secondary always take N2. But always remember, excitation means it is primary, response means secondary. But let the ratio be N1, N2, no problem. Okay.
Means for no confusion.
See, without mentioning anything, turns ratio means N1 by N2. Okay. Voltage transformation ratio or transformer ratio means N2 by N1. And in my circuit theory, K is different. That K is coefficient of coupling. Okay. But now books are also mentioning primary turns ratio means N1 by N2. Secondary turns ratio means N2 by N1. That is more clarity.
Also, you said a point that in a network and a machine there is a different point. What is that different point?
First of all, circuit there in circuit theory, L1, L2, M must be given, but in machines, practical winding will be given. That is a must be difference. And second difference is dot convention is exposed in circuit theory. Dot convention is not exposed in machines.
Okay.
And moreover, K is called here coefficient of coupling. There K is called voltage transformation ratio.
Yes. In a transformer, in a machine, we are indicating the current direction is leaving the dot.
That is a source load concept. Here, mutual aiding or mutual opposing concept.
Means here we can any type of current direction we can put.
Yes. Correct.
Okay. Thank you.
Right. So tomorrow again 7 o'clock, everybody.
Sir, hello, sir.
Tell me which will be the big day for transient. Tell me, Imtiaz.
Sir, find the power loss in 2 ohms.
Tell me what is your doubt. I understood.
Sir, in that can we write as in the circuit model?
Power lost in 2 ohms. Yes, 100% we can write. Yes, 100% we can write. Because what I will take for this mesh analysis which I took, one is entering, one is leaving.
Yes, sir.
I will take mutually opposing. Still, your I2 and my I2 will be same. But suppose you take I2 entering anti-clock, you take. Then you take mutual aiding. But your I2 and my I2 will be anti-phase.
Yeah.
But magnitude will come same.
Yes, sir. Sir, from this, the deflection finding of the I1 is difficult. That's why I'm thinking that.
No, even that is also difficult. Now, after writing T also, you cannot lump further. No use. See, you write T also, it is waste of time. Even if you write the T model and unnecessary waste of time, sir, but still you have to write two equations.
Yes, sir.
If it is pure inductor problem, then you can lump, na, but here capacitor resistor is coming, you cannot do that. Okay, right.
Thank you, sir.
Right.